Can anyone hear me?
Yes, you're
Yes.
on your roll.
Okay, fantastic. Is any other Muller candidates here who might want to try sharing your screen and make sure everything is working while we are waiting for?
I'm here, so if you
Okay,
want, I can
right.
try.
Why don't you try sharing your screen and see if everything is
Sure.
working fine? I'm still waiting for the local organizing committee to come in. Hopefully they will join in shortly. Okay, your slide one.
Yeah. So you can see my presentation slides in the presentation mode here.
Looks great. Thank you, Hina. Anybody else? I think I saw a few others also here.
Yeah, I can give it a try.
Okay.
Let me see.
Okay, this also works.
This works.
Fantastic.
Okay.
Thank you. All right. Now, who else is here?
Okay, hello.
Hi, Olga. Yes. Why don't you try?
Hello.
Hi, I can hear you. Yes.
Oh, okay, great. So I could also try to share my screen if you don't
Yes.
mind.
Yes, absolutely.
So,
Perfect. Yes, that works well.
okay, and it's changing. Everything is fine. Yes.
Yes, it's good.
Okay, great. Nice.
All
Thank
right,
you.
Thank you. Yep. Anybody else here?
Yeah, well, I'm here, but I'm not yet on the right computer. I'm actually gonna quickly run away in a minute, change computer, then come back, and I'm just gonna trust that it's gonna work.
Okay, good. And is Jeet Sarkar here? He is the first speaker.
Hi, Ruth.
Oh,
Yes, yeah, I think you can start now, isn't it?
so I think you
Okay.
had 6 more minutes scheduled for introductory remarks. So did you have anything to say to welcome back everybody?
I don't think I need to say anything. I think this session you chair, so that's
Sounds
all
good.
up to you.
Okay, thank you. All right, thank you, Professor Gangsha and his entire team who arranged this meeting. So we had a fantastic morning session. So today, this afternoon session, Beijing time, is the Muller Award competition. So we have 6 excellent speakers coming from around the world. And each of them will give half an hour. Each of them have about half an hour. About first 25 minutes of it will be their presentation, followed by about 5 minutes of question and answer from the Muller Award Committee. So the Muller Award Committee members are Sandra Taylor from PNNL, Tong Lee, from Germany. If you are all here, if you want to kind of unmute and make sure you're able to ask question, that I'll appreciate that. And Matthias Tuvander from Chalmers, Stefan Gerstel, and Katie Rice from Chemica. I see Sandy here. Is any other is any other Muller Award committee members here? Yes, I see Tong here. Hi, Tong.
Yep. Katie Rice here as well.
Hey, Katie. Is Matthias here? Yes, I see Matthias. Hi, Matthias.
Yeah, I'm here. Good morning.
Okay, I can hear you. Yes. Stefan, I'm not sure if Stefan is here right now.
I don't think I see him in the participants yet.
Okay, so the videos will be recorded, the talks will be recorded, and the Muller Award Committee will be doing deliberations afterwards, and some of them will be listening into the talks and probably asking you questions later. But in any case, our first speaker is here, Jeet Sarkar. We don't see our first speaker here. So we may have to swap the agenda in a way to, in case the first speaker is not joining within 3 minutes. Florent, are you here? Okay, second speaker is also not. I know Ranel is here.
I think I see Florent is online, but maybe he stepped away for a minute.
Okay.
Arul, I think we still have times. If I look at the timetable, I think
3 minutes.
Yeah, the session should the contested talk first one should be 13, 10 past 13. So 10 past 13. So there are still a few minutes.
Yeah, a few minutes. Yeah.
To show up. Yes, yes.
Okay. Yeah. So we can wait.
Each one have each one have the 30 minutes in total, including presentation and the question. Yeah.
Yes.
Okay.
And so just so everybody else who may be currently in university, who may not know about the Erwin Muller Award, it's an outstanding emerging scientist award, and it is the society's highest honor, and whose namesake is after the founder of the society, Erwin Muller. Emerging Scientist Award is highly competitive event. Participants should have completed a body of scientific research relevant to the society's focus, which will be presented in the presented to the entire society during the conference. After this oral presentation, the judge panel will ask participants in-depth questions, and then the final decisions will be made. Already the candidates who are selected for this oral competition were shortlisted from a larger pool of candidates based on their written application. So is Jit Sarkar here yet? I still don't see it. So why don't the Muller Award committee members introduce yourself? Sandra, do you want to go first?
Sure. My name is Sandy Taylor. I am a scientist at Pacific Northwest National Labs in Richland, Washington. And some of the special things I specialize in with atom probe tomography are the analysis of minerals. And my research is fairly diverse, where I look at how irradiation or corrosion effects on metals, to understanding biomineralization mechanisms, to crystal growth mechanisms. So I've been able to utilize atom probe tomography to investigate these processes across diverse material systems. So I'm really happy to be on the committee panel and look forward to great presentations this evening.
Thank you, Sandy. Tong?
My name is Tong Li, and I'm from Ruhr University Bochum in Germany. My key research area is about developing correlative microscopy for understanding the catalyst material, like the particles or thin films, etc., etc. Aaron, shall we send an email to Jake Carr to make sure like he knows the meeting room, etc.? I mean, now he's already one. Yeah.
Yeah. So we might skip him and we'll go to a later candidate. But temporarily, if one of you can actually send an email, that will be good to know. Fantastic. Katie, can you introduce yourself?
Yep. Hi, I'm Catherine Rice, but I go by Katie. I'm the applications lab manager at Kamika in Madison. So, you know, in our demo lab, we get to see a little bit of every material. You know, our favorite things are working on instrument development and training customers. So I'm glad to be here very early this morning.
Thank you for joining. Yeah, for you, this is the really late night. Matthias?
Hi, everybody. My name is Matthias Tuvander. I'm associate professor at Chalmers University in Sweden. working, of course, on atom probe of a lot of different things, focusing mainly on metals and nuclear materials.
Perfect. Thank you, Matthias. And the only member who is not here currently is Stefan Gustl from ETH Zurich, whom probably many of you know. Right, so I think I don't see Jit Sarkar, who was supposed to go first yet. So why don't we skip that candidate and instead go with the Florent? Are you here? No. I see you here. Probably you have stepped away thinking that it's not your talk. Is Ranel here?
Yes, I'm here. I can.
Can you go first? Thank
no
you.
problem.
Yeah, while we are waiting for others to join. So you will have a total of 30 minutes starting from now. Okay.
Okay, perfect.
All right. Thank you. Yep. So your time starts now.
Okay, thank you for having me in this Mueller competition. I'm really happy to be here. I wanted to start my presentation today maybe a little bit different than what we're used to. And I wanted to start with a quote from Rafael Pompelli. He was an American geologist and explorer. And in one of his first publications, he stated that small structures are a key to and mimic the styles and orientations of larger structures of the same generation within a particular area. So this statement became one of the basic tenets of structural geology and had become the basis of my PhD research. So in this presentation, I hope to be able to demonstrate to you that processes documented at the nanoscale in geomaterials can be used to provide information that is crucial to our understanding of larger tectonic scale processes on Earth. So one of these larger tectonic scale processes is the formation of metallic ore deposits. So in metallic ore deposits, it's well known that sulfide phases, for example, pyrite, which is an iron sulfide mineral, can incorporate significant concentrations of base and precious metals within their crystal structure, either as solid solution or as ultrafine inclusions. And had recently been suggested that the plastic deformation of these sulfide minerals can potentially lead to the segregation of these base and precious metals at crystal defects. And so one of these studies was actually my master's thesis project, where I combined EBSD mapping and laser ICP-MS elemental mapping on a deformed pyrite crystal from a gold deposit in Canada. So here at the bottom of this slide, I show EBSD grain boundary and misorientation maps of a pinch and swell structure within a pyrite grain. And we notice at the neck of the pyrite grain, or the pinch and swell structure, we have a high density of low angle grain boundaries, as well as increased misorientations. And if we turn our attention to the laser ICP-MS map, we also notice that this area is also enriched in gold. It was also enriched in other base or precious metals, including silver, bismuth, and telluride. So from this, it can suggest that the deformation of these minerals does lead to the segregation of base and precious metals at crystal defects. However, it's still poorly understood which mechanism leads to this segregation. But to explore or to interrogate these processes at the nanoscale, we require a correlative approach that involves high spatial resolution microscopy techniques. So for my PhD, I took a two-step approach. So in the first step, I conducted sample characterization and microstructural analysis, typically by combining electron backscatter diffraction mapping and electron channeling contrast imaging. So these techniques allowed me to target regions of interest for further analysis at the nanoscale. And for this, I typically combined transmission electron microscopy techniques. So this would be both TM and STM, as well as EDS or EELS analysis. And then I combined these with atom probe tomography to get the 3D dimension and have a low detection range of several ppms while still maintaining a relatively small resolvable feature size. So coming back to the remobilization of base and precious metals and sulfide minerals, I first conducted EBSD and ECC imaging to target a region of interest for analysis with atom probe tomography. So we notice here in the EBSD misorientation and grain boundary maps from a deformed pyrite grain that we have evidence of crystal plasticity in the form of a linear to heterogeneous misorientation pattern. So we have a maximum misorientation of 10 degrees, which is located mostly at grain boundaries, as well as the development of low angle grain boundaries, as well in these regions of high strain. So if we take a closer look here at the boundaries between grain 1 and grain 2, so this is the image in ECCI. So we notice that the boundary of these two grains, there's in fact a microfracture that we hadn't documented before. And when we look at the tip of the microfracture in between these two grains, which is zoomed in here, we notice that we have a high dislocation density, which are shown in these white arrows. So these are all of these bright white dots, as well as a high density of stacking faults, which are perpendicular to these dislocations, which are these discrete line segments pointed to with the black arrows. And at the tip of the fracture, we also notice that there's the development of a low angle grain boundary shown in pink and bend contours outlined in the dashed white lines. It's also important to notice that at the tip, there's also all of these black dots, which I interpreted to be most likely fluid inclusions, and these white dots, which are most likely metal inclusions. So all of these structures together made it for the perfect region of interest for further analysis with atom probe tomography. So once again, here the ECC image shows the region of interest analyzed for the APT specimen. And in the center of the slide here, I show the 3D reconstruction of the analyzed specimen, showing the distribution of arsenic ions throughout. And what we notice is that arsenic appears to be enriched in these linear structures throughout the entire specimen. And if we take a closer look at the top of the specimen, we also have a planar feature. It's not so clear in this animation here, but this planar feature was made up of several individual dislocations or linear features. And so I interpreted this to be a subgrain boundary. Now, if we take a composition profile across some of these dislocations, as shown here, we notice that on one side of the dislocation, there appears to be a depletion in arsenic, which is below background levels. So based on these observations, I came up with a segregation model for base and precious metals in sulfides, in this case where arsenic diffusion in these plastically deformed pyrite occurred mostly by dislocation impurity pair diffusion. So for this model, during recovery, we have impurities that are being attracted to dislocation cores by what is called a Cottrell atmosphere. And so during recovery, as these dislocations migrate during creep, they entrain these impurities with them, leaving behind a depleted zone and entraining them to form enriched microstructures. So by applying APT to this mineral, I was able to determine the desegregation mechanism for these base and precious metals, but I wanted to take this project even further. So I wanted to be able to develop a new processing technique that would allow for the nanostructural orientation measurement of these dislocations and low angle grain boundaries. So for this new data processing technique, it's first crucial to optimize the 3D parameters for the reconstruction. But once this is done, we first need to identify the crystallographic poles. So in the first step, we look at the detector event histogram and we look for low density areas within this map. And each of these low density areas here correspond to a crystallographic pole. So we can identify these poles by overlaying the histogram with a stereographic projection of the crystal structure of the material. So I did this mostly using the Win-Wolf program. And once I identified them, I can then plot them in the 3D reconstruction. So the XY position of the poles is determined by, by plotting a 2D contour plot that is perpendicular to the z-axis of the specimen. And by looking at this 2D contour plot, we can determine the XY position of the pole. So here I use cylindrical regions of interest to plot these poles. So once we've determined its XY position, we can go to the second step, and we need to determine its orientation or its angle. So to do this, we need to take a closer look at the crystal lattice or the crystal structure of the APT data set. And we need to find the crystallographic planes so that we can plot or orient the crystallographic pole perpendicular to these planes. So the final image should look something like this reconstruction here in the center, where I have plotted the 111 plane pole. So once you have plotted these poles, ideally for 2 or 3 poles, we can then measure the relative orientation or the relative angle between each of our nanostructures and each of the poles. To do so, or to make things a bit easier, I like to take cylindrical regions of interest and plot them through each of the nanostructures. And then I use a program such as ImageJ, for example, to really look at the angle between them. And once we determine the angle or the relative angle of each structure to each of the poles, we can then plot them on a stereographic projection for further analysis. So in the case of this study, I noticed that most of the dislocations appeared to plot either along or really near to the 110 planes. And so this allowed me to conclude that deformation in the sample was accommodated mostly by dislocation glide and creep processes with slip occurring along the 110 planes. So I wasn't able to determine the specific Burgers vector or the orientation of the slip system. However, by using other slip analysis in ECCI imaging, I was able to confirm that the slip system for these samples was truly 110 with orientation in 001 direction. So from the data I just showed you, I think it's fairly clear that deformation plays a very important role in the remobilization of sulfides and potentially the formation of metallic ore deposits. The issue is that we still don't really understand the deformational behavior of sulfide minerals. And this is especially the case in the presence and with the interactions of nanostructural defects within the sulfide minerals. And one of these nanostructural defects that is very common in metallic ore deposits or sulfides within metallic ore deposits is fluid inclusions. And so for this next part of the project, I wanted to investigate the influence of these fluid inclusions on the rheology of pyrite. And so to do this, I first identified a pyrite crystal that was rich in fluid inclusions from the same sample. And so here in the STEM image, we noticed that we have all of these low density areas. So these are all the fluid inclusions in the pyrite crystal. I then did EBSD mapping on these crystals to target a region of interest that had very minor crystal plasticity. So I was looking for fairly undeformed crystal so that the only feature that I was looking at with APT was really the fluid inclusions and no other defects. So I selected this region for atom probe tomography. And here's the reconstruction. So in this reconstruction here on the left side of the slide, the pink dots represent iron atoms or ions, whereas the turquoise envelopes or turquoise isosurfaces represent regions enriched in arsenic, and the red isosurfaces represent regions enriched in oxygen. And we noticed throughout this data set that we have these ubiquitous arsenic and oxygen enriched clusters. So if we take a closer look at one of these clusters here, we notice that they are mostly made up of a arsenic enriched sphere and overlain by an oxygen enriched disc-like shape. And if we take a composition profile across one of these features, we notice that these clusters also correlate to high point density features within the data set. So to confirm that these features that we've documented are truly fluid inclusions, our collaborators at the Groupe de Physique des Matériaux in Rouen conducted some field evaporation simulations. So in this case, they used a meshless finite element method to simulate field evaporation of a specimen containing fluid inclusions. So in this case, the specimen geometry was simplified to a hemisphere on a cylinder with a simple cubic crystal structure. So the lattice parameter used for these simulations was 0.2 nanometers. And the fluid inclusions here were simplified to core shell particles in a pure matrix. So the core particles were to represent loosely bonded particles or atoms that form a fluid. So for this case, they were assumed to have a very low or significant lower evaporation field, so 10% that of the matrix. And the shell here was assumed to be a mix of both shell atoms and matrix atoms, where the shell atoms had a slightly higher evaporation field than the matrix. So here the shell atoms are assumed to be arsenic, which form the coating of the fluid inclusions. So for these simulations, we varied the size or the ratio of the diameter of each of the fluid inclusions relative to the curvature or apex of the sample. And so by varying the size of the fluid inclusions as well as the compositions of the shell of the shells, we were able to have a total of 6 simulations. And for each of these 6 simulations, it led to a very similar post-evaporation morphology, as you can see here. So here we noticed that the shell atoms seem to have mostly maintained their spherical morphology, just slightly erratic arrangement of atoms. But what we notice is that the core atoms here have all formed these dense disc-like shapes, either on top of these spheres or at the edges of the spheres. So now these morphologies or these structures are very similar to what we've documented in the APT experiments. So these morphologies can easily be explained with ion trajectory aberrations. So on this slide, I wanted to show a schematic to show you what happens during the field evaporation of a sample with a fluid inclusion. So in image A here, we have a pure matrix with a fluid inclusion in the center, and we start evaporating the surface of this sample. And so at first we have matrix ions that are evaporating at 90 degrees from the surface, and then are compressed as they follow the electrostatic field. And this results in a homogeneous density of hits on the detector here. In image B, we start to evaporate matrix and shell ions, and since they have a very similar evaporation field, they evaporate at approximately the same rate, and they hit the detector at a homogeneous distribution. So again, we still have this homogeneous density of hits. In image C here, we now expose the core of the core shell particle or of the fluid inclusion. And since these core ions have a much or significant lower evaporation field, they evaporate at a very fast rate, almost at once. And this results in a localized high density of hit on the detectors here, shown by this dark area. And since they evaporate at once, we don't have time to register their Z dimension for the 3D reconstruction, which is why it leads to these oblate or disc-like structures. So then in image D here, once we've evaporated all of the ions from the core, we are left with shell ions, and they evaporate 90 degrees from the concave surface here, which results in their converging flight paths and also leads to a high density of hits on the detector. So this leads to these features as being high point density features and spherical clusters on the 3D reconstruction. So with these simulations and with the experimental data, we have been able to successfully characterize inclusions in APT data. And so we were ready to now investigate the influence of these fluid inclusions on the rheology of sulfide. And so here for this next step of the project, I wanted to select a highly deformed or a deformed region of interest within the pyrite crystal to be able to analyze the influence, or to be able to look at the interactions between fluid inclusions and other crystal defects within the mineral. So in this EBSD misorientation and grain boundary map here, we notice that there is evidence of crystal plasticity in this sample, form of a heterogeneous misorientation pattern with maximum misorientations of 8 degrees, mostly localized in the center of this grain, and apparent low angle grain boundary development in these higher strain domains here. Now I say apparent because if we turn our attention to the ECC images, we notice that these low angle grain boundaries are in fact microfractures. And so this is shown here by these very discrete line segments. So these are not low angle grain boundaries. However, if we look at the tip of these microfractures, we notice that there is still dislocation walling, which are mostly propagating from these microfractures. And on top of all of this, we notice that there's a clearly high dislocation density in this higher strained region, as well as further away from the crystal. And so based on these images and these EBSD map, I selected a region of interest in the center of this high strain region for further analysis with APT. So here, the animation on the left shows the 3D reconstruction of the specimen. Once again, the pink dots represent iron ions, whereas the turquoise isosurfaces represent arsenic and red isosurfaces represent oxygen. And we notice in this reconstruction that once again, we have all of these arsenic and oxygen enriched clusters. And if we take a composition profile across one of these clusters, or these features, we notice that there's also enrichment in sodium and potassium. So sodium and potassium are common elements that are found in aqueous brines that form fluid inclusions in the context of metallic ore deposits. And so this reaffirms that these features, once again, are truly fluid inclusion. So if we look at these larger fluid inclusions here, for example, in the box here showing structure 1, we notice that these larger fluid inclusions appear to be linked together by arsenic-enriched linear features or arsenic-enriched dislocations. So to confirm this configuration, I also wanted to look at a similarly strained region in an adjacent crystal with STM analysis. So here are the STM images, and we can see in these images that we have fluid inclusions everywhere. So these are these darker spherical features. And we also have dislocations in the form of these curved or bowed line segments. And what we notice once again is that each of the large fluid inclusions appear to be linked to dislocations, either 1 or 2 dislocations. And they also appear to have a bright contrast in the STM images, suggesting there is a segregation of the heavy element in them. So based on these observations, I came up with a new fluid inclusion induced hardening model. So in the first stage of this model, dislocations migrate during creep processes, and they then become pinned by arsenic-enriched fluid inclusions as they encounter them. In the second stage, the portion of the dislocation in between the pinning points can continue to migrate during creep, which is what leads to the bowed or scalloped configurations that we documented in STEM. And then lastly, in the third stage, we have arsenic from the fluid inclusions here that can migrate, move into the dislocation cores by pipe diffusion, which leads to a reduction of the stress field as well as the elasticity of the dislocation, stabilizing it and leading to further immobilization and local hardening in the mineral. So these findings were in contrast to the most commonly reported softening or weakening effect of fluids in minerals. So here I just wanted to summarize some of my key findings during my PhD thesis. So I was able to, by applying APT, analysis, I was able to identify the diffusion mechanisms that lead to metal segregation in crystalloplastically deformed sulfides. So this is very important as it can lead to the formation of viable economic deposits. I was also able to develop a new data processing technique, pushing the limits of APT, to determine the crystallographic orientation of the nanostructural defects using the APT data alone. And I was also able to document the first direct evidence of nanovoids, or in this case, nanoscale fluid inclusions in geomaterials, as high point density features in both experimental and simulated 3D APT specimen reconstructions. And this finding, or this achievement, led me to document two processes that, when combined, led to proposing a new model where fluids can have a hardening effect on minerals rather than the more commonly reported weakening effect. So thank you so much for your attention. I would also like to thank my PhD advisor, David Schneider from the University of Ottawa, as well as my mentors, Anna Hogovitz from the University of Vienna and Batsisco from MPIE. So thank you.
Great, perfect timing. Now we have 5 minutes of question answer from the Muller Award Committee. So Muller Award Committee members can actually unmute yourself and ask questions.
Yeah, so I could start. Thank you very much for a great presentation of fantastic work. So some questions. First, did you find any gold?
Unfortunately, no, I did not find any gold in these samples. There was gold in the laser ICP-MS maps, but I'm thinking maybe the concentrations were too low, or maybe it's very localized. And since the specimens for APT reconstruction or APT analysis are very small, maybe I simply missed these areas as they tend to be very heterogeneously distributed. But arsenic is very closely linked to gold in these systems because the arsenic content in sulfide minerals significantly increases the solubility of gold within these minerals. And so my hypothesis is that if arsenic segregates into these nanostructures and becomes concentrated into these nanostructures, then this depletes the matrix of arsenic. So maybe by depleting the matrix of arsenic, we are reducing the solubility of gold within that matrix, and this might lead to the exsolution of gold. So that was previously as a solid solution or within the crystal lattice, they might become ultrafine fluid inclusion, ultrafine metal inclusions. So I wasn't able to find that yet, but.
Right, thanks. When you showed the figure with the pole figure or crystallographic projection there, you have a few points and you say they are within ±5 degrees of the 111 planes.
Yeah.
Do you mean that there is a deviation from that, or is that sort of representing the accuracy of this approach?
I think it's mostly related to the accuracy of the approach. I really do think that this could be a very robust method depending on the material that you're studying. So geomaterials it's usually very difficult to get crystallographic poles or crystallographic planes within your 3D reconstructions or your data sets. So the fact that I was even able to get this trend with pyrite was really an achievement, I think. But I think we could easily apply this to other materials that may have clearer detector event histograms, and this would significantly reduce the error. And the more research we do and the more we optimize 3D reconstruction parameters, I think the more accuracy we can get with this approach.
All right, thank you. I leave to Sandra.
Thanks, yes, and great presentation, Ranel. I guess following up on this poll figure, I was wondering how you determine the 111 direction, and then also the assignment of the, if I'm understanding this correctly, 111 planes at the shank of this reconstruction.
So you're okay. So to determine the poles, to identify each of the poles, I simply overlaid the histogram with the stereographic projection of the FCC crystal structure. But to confirm each of the poles identification, I also reconstructed the data set along each of these poles, and then compared the ratio of the lattice spacing along each of these poles. So I compared the measured lattice spacing along 002 to the measured spacing along 111, and I compared this to the ratio of the theoretical values. And so even though my reconstructions for the first, for the measured lattice spacing weren't accurate yet, the ratio of the lattice spacing between the two poles should have been the same as the ratio between the theoretical values. And so with this, I was able to confirm that they truly were correctly identified.
Okay, thanks for that clarification and explanation. One other question I had was, in your simulations for the fluid inclusion structures, where I guess you show this example of them being core shell-like structures. I was wondering how you expect evaporation in real, or how evaporation would be different in your specimen. Should the ions be randomly distributed in the inclusion? So rather than having this core shell type structure, what if arsenic and iron, or arsenic and oxygen, were just mixed together? Would that still lead to these oxygen shells or arsenic shells? And
yeah, I think if, for example, if arsenic was like contained within the fluid, then I would expect it to, since it would be loosely bonded particles or atoms, I would expect the arsenic to also form these disc-like shapes at the top. And then I would expect the spheres to be mostly probably iron, because that would be what would be along the surface or the concave surface. So yeah, because otherwise I think if arsenic would be contained within the fluid, then it would be also enriched in these discs. Yeah.
All right. So I think actually, in the interest of time, we might move on to the next candidate. But Ranel, if you can hang around, we may have finally a time for a question answer at the end again. So committee, maybe hold off your questions until all the candidates present. Okay, thank you. All right, so next candidate is Florent. Are you here, Florent? Perfect. Why don't you share your screen?
Let me see.
Okay. Yes, we can see it. Okay, your time starts now. Great. Thanks.
My name is Florent. Today I will present my work on an aerotopic scale analysis of hydrated materials using graphene cutting, which I conducted during my PhD at the university under the supervision of Respective. So first, Russian revolution. We'll talk about a special technique we use, which is graphene cutting, and how we try to understand the effects of graphene cutting on the activities.
So, Florent, I think your audio is not very clear. It's kind of breaking up. I'm guessing, I mean, if your headphone battery is low or something, maybe that is what is causing it. I'm not sure. If you can change the microphone and try again, that might be better.
Now, can you hear me?
That
Better?
is much better. That is way better.
Okay,
Yes.
but I cannot hear you anymore. Okay, how about now?
Yeah, we can hear you.
Okay, I cannot. I for some
Keep
reason
going.
I cannot hear
Keep
anymore.
going. You keep going. Keep going.
Okay.
Oh, now we cannot hear you at all. Okay. We cannot hear you. We cannot hear you actually. So I think your voice was better when you went to the other option. I suspect your headphone battery is low or something is going on. Probably switch it off and use the computer. No, still not good. Can you speak?
Yes, about now?
Yeah, now we can hear you. Yes.
Now you can hear me? All right.
Yes.
Slow down or keep going?
Maybe you have to close to speaker.
Yeah.
All right. Stay down.
Okay, so it's kind of breaking up a little bit. Maybe stay close to the microphone and then try speaking. If you want to switch off the video for better audio, that might be better. Okay.
If I speak close to it now?
That's better. Yes.
Okay. All right. Perfect. All right. So after having a look at the graphene encapsulated water studied with atom probe tomography, we will have a look at the rehydration and atom probe analysis of E. coli cells enabled by graphene coating as well, and then some conclusions. So understanding the nanoscale structure of biological materials is essential to help solve some of the modern health issues, such as antibiotics resistance, for example. Several methods have been employed in the past to try and provide chemical and/or 3D structural analysis using tomographic methods involving the removal of thin layers of materials using ion milling. However, none were able to provide both chemical and structural information at the same resolution as atom probe tomography. At the time when this project started, several studies had been conducted on biological materials, such as on mammalian cells, human dental enamel, or dried bacterial cells, for example. And this last one in particular was studied using graphene coating, which is a preparation method that increases the conductivity at the tip of an atom probe specimen. And in this case, it was used to conduct voltage pulse analysis of the bacterial cells, thus avoiding potential thermally induced damage from laser pulsing. With this project, we aim to bridge these two distinct fields, so atom probe tomography and biology, and push the boundaries of atom probe applied to biology. Since we started this project, a lot of work has been done, as can be seen on this slide, showing atom probe studies on biological and/or hydrated materials that were published in the last couple of years. And I have to admit, I couldn't be more excited to be part of this international effort. I think this is great, and that's it. So let's move on to graphene coating that I mentioned before. So in this study, it was used to improve the conductivity of a non-conducting sample. I will explain a little bit about this later, but here's a brief overview of how it works. So I purchased the graphene as chemically vapor deposited on copper foil. So the copper needs to be removed using chemical etching. And at the end, we obtain a graphene foil that's floating at the surface of water in a Petri dish, like this. Then the graphene foil is scooped using a wire loop and then applied to the tip of an atom probe specimen. In the case where liquid needs to be analyzed as well, we can add a little volume of liquid to the solution, and then the graphene foil with the liquid are dropped and applied on the tip of the specimen. And in the case of encapsulation of liquid, the volume is determined by the coating speed. In our case, we used a special device to control the coating speed, which is right here, and with a control box, which enabled us to tweak the speed. And in our case, the lowest speed that was used was 0.02 millimeters per second. And this is what it looks like up close. But of course, it's also possible to do manual coding. Just it doesn't enable us to control the speed, but it still works. And some of the results presented in this presentation were obtained with a manually coded sample. So here we can see a tip before graphene coating right here, and the same tip after it was coated 4 times with graphene, and then again the same tip imaged after atom probe analysis. So firstly, we can see that the graphene drapes the specimen like bed sheets and takes quite some space compared to the initial volume, and also as shown here on the atom probe monitor screen. However, during the evaporation, we can see that the graphene protrusions change or get removed throughout the acquisition. So that answers part of the question, what happens to graphene? Although some of it can be caught by the detector, parts of it can just fly off the tip. And just for reference, this is what a normal sample usually looks like on the atom probe screen in comparison to the graphene coated one. So the first step of this study was to analyze pure tungsten coated with graphene to try and understand the effects of graphene coating on a well-known test material. So this is a schematic of what the sample looks like prior to atom probe analysis. So we've got a layered structure with the tungsten, thin layer of oxide, and then the water, graphene, and then repeat with additional graphene layers. And this is what the 3D reconstruction of such a tip looks like. So these images here, they come from successive 2 nanometer thick cross sections, and we can clearly see the graphene draping the tip of the specimen, as highlighted by the rings coming from the successive cross sections. So several samples were coated in this way, with varying numbers of graphene layers in order to study the impact of multiple layers versus one single layer on the electrostatic field. So prior to graphene coating, the tips were pre-run in the atom probe up to 5 kV to clean the surface and also to provide shape consistency from one sample to another. So this is the mass spectrum from the pre-runs, which is fairly clean with just a little bit of hydrogen and tungsten 3+ and 4+. And these are mass spectra coming from the multi-coated specimen and a single coated specimen. The key points highlighted by these mass spectra are first, the detection of carbon atoms from the graphene, which were also shown in the previous slide. So it peaks at 12. We've got C, we've got CO at 28. Then we have the second point is the presence of tungsten in the 2+ charge state, as can be seen here in both samples, which indicates a lower electrostatic field. And finally, we have the presence of copper, which is essentially contamination from the graphene coding protocol, but in this case was used as a proxy to estimate the electrostatic field variations. The electrostatic field was estimated for the single coated layer specimen and the multiple coating layer specimen using the charge state ratios of tungsten and of copper when applicable. And a lowered electrostatic field was measured for the sample with several coating layers compared to the single coating layer, which is in line with our initial hypothesis. After studying this tungsten test sample, the next natural step is an actual non-conductive liquid sample that can benefit from the amazing effect of graphene coating. And this is where we start the analysis of the atom probe analysis of hydrated biological materials. So the actual goal was to achieve near native hydrated state analysis of biological materials in the likes of what has been done in cryo-TEM. However, it's quite complicated and challenging. So here we separated the problem in two distinct ones. The first one is hydrated material, no biological, and this is pure water. And the second study is on hydrated biological material, but not really in the near native hydrated state. But actually the samples were dried and then partially rehydrated using graphene encapsulation. And the samples used in this study were sections from single E. coli bacterial cells. So first, let's have a look at the study of pure water with graphene coating. So there several workflows were compared. So first, the basic one, if I may, where graphene encapsulated water on top of tungsten tips was transferred directly to the atom probe using normal room temperature transfer. And the results were compared to cryo workflows that were conducted at the University of Sydney with the help of Microscopy Australia. And two different scenarios were studied. So scenario A, both scenarios start with plunge freezing of water graphene encapsulated on top of tungsten tips. And for scenario A, we have direct cryotransfer to the atom probe using specific cryotransfer tool that I will describe later. And for scenario B, after plunge freezing, the samples were transferred to the cryofib to try and remove the graphene to see if there's any difference without the graphene and see if we can keep the water on the tip, and then cryotransfer to the atom probe. So two instruments were employed. The first one was a LEAP 5000 with a reflectron at Deakin University. And the second one was a LEAP 4000 with a straight flight path detector. And so the two operational modes were compared. So at Deakin, we only did room temperature specimen preparation and transfer. But in Sydney, we did room temperature and the two different scenarios that were mentioned before, cryo scenarios. And for each conditions, we compared as well laser pulsed and voltage pulsed. So these are the number of runs that were obtained with each scenario. So for the cryo workflows, as I said, they were conducted at Sydney Uni and with the help of Takanori Sato, Levi Teg, and Li Mei Yang, who I all thank very much because that was great help. And using equipment that is already presented in the literature, so essentially cryotransfer suitcase that can transfer samples between the glove box, the atom probe, and the FIB. So first overview of the cryotransferred samples was, well, unfortunately, some tips were covered in frost, as here on the left. But since we were using the FIB, we were able to remove some of the frost and hopefully target the tip of the specimen and remove the graphene, which was achieved by Li Mei. And so here is an overview of the atom probe results from a sample analyzed the scenario A with voltage pulses, meaning that, again, the sample was plunge frozen following graphene encapsulation and then transferred directly to the atom probe and analyzed. In the 3D reconstruction, we can see the successful detection of water-related ions, such as H2O and H3O at the tip. And here are the voltage evolution and the detection rate, as well as the mass history, showing the evaporation sequence. The evaporation of water always started at a relatively low voltage, sometimes plateaued for a bit, and then increased once the water was removed. And here we have several optical images that were taken in situ of the atom probe, and that corresponds each to the vertical lines in orange, purple, and blue. And we can clearly see that there was a bit of frost building up at the tip, but that it was clearly removed. And after that, we were still obtaining some strong water signal. So now let's have a look at the mass spectra. So the main point is the peaks corresponding to graphene, so with carbon, for instance, and to water that were detected in almost each data set. Another key aspect to note is that there are no molecular ions corresponding to water that are larger than 45 Dalton, as opposed to other atom probe studies on larger volumes of water, where the heaviest detected ions went beyond 100 Daltons. In this work, the peaks heavier than 45 come from the tungsten substrate and also occasionally the copper from the graphene etching. So here we have the mass spectra from the reflectron instrument at Deakin with room temperature transfer, with a relatively greater number of water-related ions, mostly what is here in this area, that were detected compared to other data sets acquired on the straight flight path instrument. These two mass spectra are relatively similar, the main difference being the charge state ratio of various ionic species. So for example, for tungsten, we have a higher amount of 4+ with the voltage experiment rather than with the laser one, which can be explained by changes in the electrostatic field due to the acquisition conditions. And also, there appears to be fewer peaks for the voltage pulsed experiment, which can be explained by the higher field, which causes evaporation as lighter ions due to field-induced molecular ion dissociation. Unfortunately, these two data sets obtained on the straight flight path instrument at room temperature had the smallest number of detected ions, especially in the voltage pulse data sets. So comparison is difficult, and I'm not going to spend too much time talking about it. And then for the cryo scenarios, the first point to note is a slightly better yield compared to the room temperature scenarios on that instrument. And the second point is that although some frost could be seen at the tip of the specimens, the samples could be analyzed regardless, and there are noticeably fewer peaks than for the room temperature experiments. For cryo scenario B, the absence of peaks containing carbon, so at 12 or 28 or 29 with CO and COH, seems to confirm the successful removal of the outer graphene layer, which is in the film. So the key findings of this part of the study on water is that we were able to single out the composition of graphene encapsulated water, which was essentially OHX plus ions with X between 0 and 3, and carbon with C plus, CO plus, COH plus coming from, well, the graphene. But also we realized that these three species were actually in reduced amounts after cryofib removal. The cryo preparation was challenging due to damaging frost buildup, but nevertheless, we had seemingly better yield with the cryo workflows. And finally, an observation on the parameters that were used, lower pulse frequency seemed to be better. Moving on to the next step of this dual problem of hydrated biological materials is the analysis of E. coli cells So the cells were dried and then prepared using fib lift out, and then graphene encapsulated using the same method as described earlier. And so here, first we have the detection rate right here and the voltage evolution. So there's a clear initial first stage where the detection rate remains stable, close to the set target, and then the voltage increases here in this area. And at the end, it increases even further until we reach the tungsten substrate. So the data set is divided in 3 clear parts, and here we focus on the first one in the green rectangle. So this is the mass spectrum from this part of the data, and we see many peaks up to 90 Dalton that were detected. And these can be grouped into families of organic molecular ions with varying number of carbon atoms. So here we have C4 group, C5, etc. And besides the organic ions, all of the ions that were identified earlier as being part of the signature of graphene encapsulated water, so including carbon and also water, were detected. So although no significant structural information, unfortunately, as can be seen in those reconstructions, was identified, the partial rehydration of water was confirmed. The partial rehydration of the cell was confirmed. And the amount of water was estimated between 5 and 15%, depending on the peak assignment scheme. But this was the first time a hydrated cell were analyzed in this fashion. So the key findings from this part of the study are the successful rehydration of a dry bacterial cell that unfortunately we were only able to obtain limited structural information, but we were able to confirm that the detection of peaks related to organic material stemming from the bacterial cell. And now to conclude, so this study was separated in 3 axes, and the first one was trying to understand the effects of graphene coating on an atom probe specimen. And we realized that the electrostatic field was decreased in the presence of graphene, and the effects were increased with multiple graphene layers. Then we had a look at water that was graphene encapsulated on top of sharpened tips. And we found few large molecular ions as opposed to other studies with pure water. And we had a look at combining graphene encapsulation and cryo workflows, which had never been done before. And I think it's a promising approach, although we had limited time to carry out these experiments. And there certainly is more to be done, ideally, without restrictions due to another pandemic. And finally, we had a look at E. coli cells, and we were able to confirm the rehydration of dried bacterial cell by graphene encapsulation. So thank you for your attention. I want to thank my supervisors and everyone who supported me in this project. So I will answer any questions, or if this presentation is recorded, feel free to shoot me an email. Thank you.
Perfect. Thank you, Florent. That was perfect timing also. Now I will hand it over to Muller of our committee to ask any questions you have.
Thank you.
Yep.
Hello, Florent. Thank you for your presentation. So I think this is an exciting study. We are talking about using atom probe to analyze the biomaterials. So the case you have is the E. coli. And if we look at the chemical formula of this a molecule, I mean, essentially it has a very, very big mass. It's something like over 800, but the mass spectrum you analyze is mainly something like the species below 100 DA. I'm wondering, how can you make sure the peaks you're analyzing here is the part from the E. coli, or this is how did you distinguish that it's not the impurities like during the, say, plantar freezing or during the graphite capping?
So when it comes to graphene coding, I really analyzed a lot of samples, and the fact that I never got any peaks in this way higher than 45, as was mentioned in the water study, to me indicates that at least it doesn't come from the graphene coating. And as far as impurities go, so as I showed here, so we tried to I tried to target the E. coli cells with as much precision as possible. So using actually the platinum button deposition that was described in another work, and we really did our best to target the cells with the utmost precision in this way. And I have to admit that gauging the presence of the sample in the Z direction during the annular milling was quite challenging. But there was a big difference between this sample in particular and others, where either I just missed the sample completely and got either pure platinum and then that was it, or I removed too much and I hit the silicon or the tungsten directly. And to me, it seems pretty convincing that that in this case we were right into the cell, and that's also confirmed by the sort of entanglement. I don't think this is the right word, but of the water and the cell. I'm not sure if there was any other type of material on there, whether it would be entangled in such a way in the results.
Katie, do you want to go ahead? I have some other, I can go afterwards.
Sure. Since we're on the slide, first I want to ask, maybe an E. coli bacteria is a couple microns wide, something like that from this. So what do you think that atom probe on the nanoscale could bring to the understanding of E. coli? What information do you think that atom probe would add to this biological study?
So a lot of studies on bacterial cell involve nanoscale, the analysis of nanoscale information. Initially in this project, some of the motivation was the study of antibiotics resistance, and which was discovered to be related to the structure of the membrane of the cells. And in this case, that's what we were trying to do, was trying to target the membrane, which is actually why here from this single cell, I tried to obtain two different samples, one at the edge to try and see the structure of the membrane, and one in the middle as well. And this is where it has a potential to help to highlight some nanoscale structure on the membrane, or also on other different parts of the cells, which there has already been this type of information provided by electron microscopy, for example, TM in this case. But here we're trying to provide three-dimensional information and structural information.
So would there be a chemical difference between the antibiotic resistant and the non?
Yes, absolutely.
And what is that chemical difference? Is the carbon going to help you with this?
So in this case, it was part of the difference was in the was highlighted by the type of proteins that were detected, and that was gauged by the amount of phosphorus. So that was not done in my in this work, right? We were trying to obtain rehydration of the cell as well to try to get a state of the cell that was closer to the native state. And in this case, I myself didn't perform any comparison between antibiotics resistant and susceptible bacteria. So yeah, my ability to answer this question is a little bit limited, but yeah.
Well, thank you for trying. Okay, Tong, I know you had more questions.
Yeah, so actually, maybe Tom, can you hold the questions that
exactly. Yeah, let's continue. Yeah, sounds good.
Awesome, thank you. So Florent, if you can hang around until the last speaker, we'll have a common time for the Muller Award Committee to ask questions to all the speakers. So if you can hang around, that'll be fantastic. Thank you.
All right, thank you. Thank you very much.
Fantastic. Okay, Hina, are you online?
Yes, yes. So
can you share your screen?
I hope you can hear me and see my screen. If that's not the case, please let me know if there is any interruption.
Yes.
Hello, everyone.
Yep. Go ahead. Thanks.
Thank you for joining my talk. I am Hina. I have recently joined as a postdoctoral researcher at FAU Erlangen last week. So the work that I'll present today is based on my PhD thesis that was done at Max Planck Institute for Eisenforschung in Düsseldorf, which was based on the investigation of hydrogen embrittlement in a high manganese twinning-induced plasticity steel. Before I begin, I would first like to thank my collaborators, the amazing team at MPIE and the team at Karlsruhe Institute for Technology. So let's start with, let's start with what is hydrogen embrittlement. This phenomenon has been known for more than a century when it was first discovered by Johnson, that when a piece of steel is exposed to the hydrogen-containing environments, its physical and mechanical properties change, which leads to its embrittlement. And since then, hydrogen embrittlement has led to several catastrophic failures, such as the collapse of the Oakland Bay Bridge in San Francisco and the oil spillage in the Gulf of Mexico, both of which were due to the failure of connector bowls, which were not resistant enough to hydrogen embrittlement. High-strength steels are particularly susceptible to hydrogen embrittlement. So we chose a twinning-induced plasticity steel with this composition for the current study, because it is a high-strength steel in the uncharged state. When it is not exposed to hydrogen-containing environments, it has the high tensile strength of about 700 megapascal and high ductility. But when it is exposed to the hydrogen, such as after 5 days of cathodic hydrogen charging, its ductility was drastically reduced to about 10%. So to investigate further, we tried to examine the dislocation structure at intermediate levels of tensile strain. And we observed that in the hydrogen charged sample, which was deformed to 3% strain, there was the formation of dislocation cells. While at higher strain, at 7% strain, there was the formation of stacking falls. And these features were not observed in the uncharged sample at these deformation levels. There was dislocations which were observed in the uncharged sample at both of these strain levels, which did not form any features such as dislocation cells or stacking falls. So this shows that hydrogen modifies the deformation mechanism, but how it modifies that, it is not yet clear, like whether hydrogen is segregated at these grain boundaries or it is segregated at these dislocation structures. So to answer these questions, we had to find ways of analyzing these site-specific microstructural features with hydrogen by atom probe tomography. So for this, we explored several methods. One of them was electrolytic charging for charging the atom probe specimens with hydrogen, which is conducted in this electrolytic cell. So here electrolyte is used as a charging solution, and the sample mounted on this cryogenic puck is connected to the cathode, while platinum wire is used as anode, and there's a reference electrode. Alternatively, we also developed the gas charging method in the gas charging chamber, which we called as the reactor hub module. So firstly, I'll talk about the electrolytic charging method, which was conducted in this setup. And for this, the conventional atom probe geometry of the silicon coupon mounted on a copper strip cannot be used, because for this, the copper clip will first go into the solution and will react with the charging solution. So molybdenum half grid, which are typically used for TEM specimens, were used for mounting these specimens. And then these grids were mounted on the grid holders, which were connected to the cryogenic puck, which was immersed in the solution. So also for this, we prepared the thick platinum wells of the sample on the molybdenum grid pose, because the samples which are sharpened to the APT specimens will also dissolve into the solutions. So we first prepared the thick platinum wells, which were charged in this electrolytic cell in glove box by deuterium. And then they were quenched into this glove box, and then they were transferred via the pre-cooled suitcase to the FIB, which is equipped with a cryogenic stage, to mill these specimens to the atom probe specimens for further analysis at cryogenic temperatures. However, electrolytic charging had several issues. Either there was the frost on the molybdenum grid, or the platinum wells were too weak to survive the charging and quenching conditions, and when they survived, the sample was corroding in the charging solution. So we alternatively developed the gas charging method in the gas charging chamber, and we had to develop this setup for that charging, which really worked in the end. So in this reaction chamber, the specimens can be treated in the presence of introduced gases at high temperature, for which it is equipped with an infrared laser, which is used to heat the APT specimens. And suitcase can also be connected to this reactor hub module to allow the ultra high vacuum transfer of these specimens. So here is the deuterium gas charging workflow which was followed. An atom probe specimen containing a specific microstructural feature in this grain boundary is first transferred to the atom probe, where it is analyzed until the grain boundary feature is seen. This is to collect the data before and after charging, so that the hydrogen coming from the specimen can be distinguished from the hydrogen coming from the analysis chamber. And then it was transferred in the suitcase to the reactor hub module for charging. So I would like to briefly show this process using the videos that we recorded. In this, the sample is already pre-analyzed up to the grain boundary, and then it is transferred to this suitcase at the atom probe. And then this suitcase is detached from the atom probe, and it is connected to the reactor hub module. And then we transfer the sample from the suitcase into the reaction chamber. Then deuterium gas is introduced into the chamber, and then we start the charging. After this, we wait for some time. For instance, in this case, we perform the deuterium charging for 6 hours at room temperature. And after the charging, it was quenched in the suitcase, and then it was transferred through the suitcase to the atom probe for further analysis. So this procedures also I would like to show using the video. And in this case, after the charging was finished, then the sample is transferred from the reaction chamber into the suitcase. And then we disconnect the suitcase and attach it to the atom probe. After this, we already have the pre-cooled cryo jog in the analysis chamber. This is to maintain the cold chain of the workflow. So here this cryo jog is first transferred from the analysis chamber into the buffer chamber. And the sample is transferred from the suitcase onto the cryo jog in the buffer, and then it is transferred from the buffer chamber into the analysis chamber for further analysis. So this protocol was followed, for instance, on this sample, in which we confirm by the transmission Kikuchi diffraction that these are 2 grain boundaries in this sample with these misorientation angles. And we first did the pre-analysis, and in this pre-analysis, when we saw that the grain boundary has evolved, then we stopped the analysis and we transferred the sample to the reactor hub module for charging. And after deuterium charging, we observed the segregation of both deuterium and oxygen at these grain boundaries. Now here there were 2 grain boundaries and both of them were faceted. So I'm showing the composition profile across one of the facets, in which we had the enrichment of deuterium and oxygen with the depletion of manganese. And we have the pre and the post charging data to compare the field evaporation conditions of the analysis. So for which we use the charge state ratios as proxy, and which shows that the field evaporation conditions were uniform for both the analysis. And then we performed the similar analysis on the sample with dislocation cells, which were formed in the 3% strain sample after hydrogen charging. So we prepared an APT specimen from the region containing very high density of dislocation cells. But we could not find any deuterium segregation at any specific microstructural feature. It could also be because the samples were already charged first with hydrogen and then they were subjected to the tensile test. So possibly all these sites could be occupied by hydrogen. For this, we also mapped the hydrogen distribution in the sample, and hydrogen was also not segregated at any specific features. So we also plotted the frequency distribution analysis, which shows that there was no segregation of deuterium or hydrogen at any specific feature or at any dislocation. Similarly, we performed this analysis on the sample with dislocation with stacking faults, which were formed at 7% strain. So we prepared these samples from the region with stacking faults. And at that also, we could not find any segregation of deuterium at any stacking faults. So this simply shows that there is a modification in the deformation mechanism by hydrogen from the formation of dislocation cells to the formation of stacking faults. But hydrogen is not really segregated at these dislocation cells or stacking faults or at any of these dislocation structures. But its segregation at these grain boundaries modifies the deformation mechanism. So I would like to briefly explain this mechanism. Here is our stress strain curve of the charged and the uncharged samples. And now I would like to show only the region of the stress strain curve only up to 10% of strain because the hydrogen charged sample fractures at 10%. Here is the one. And here is our microstructure with grain boundaries. When we charge it with hydrogen, hydrogen is segregated at all these grain boundaries, and which is why it delays the dislocation nucleation from the grain boundaries by delaying the Frank-Fried source mechanism, which is why there is an increase in the yield strength after hydrogen charging. With a further increase in the applied load, multiple slip systems are activated because in order to cause any deformation at these small levels of applied load. That's why there is a plateau at after the yield point, and due to which the dislocations are nucleated from the non-planar slip systems, means they are nucleated in all possible directions, which interact with each other to form the dislocation cells, which were observed at 3% strain. And then when we further increase the load, there is a redistribution of hydrogen in the microstructure, because there are more dislocations which are nucleated from non-planar slip systems, and then there is a redistribution of hydrogen in the microstructure, which breaks these dislocation cell walls, and it nucleates the stacking faults locally, because this redistribution of hydrogen creates the regions with lower and higher hydrogen contents. And there are regions which are depleted of hydrogen, and there are regions which are enriched in hydrogen. And hydrogen reduces the stacking fault energy. So the regions which are enriched in hydrogen, locally the stacking faults are nucleated in those regions. And these stacking faults, which are observed at 7% of strain, they stack together to form these epsilon martensite plates. These plates are impinged in between grain boundaries, which lead to the embrittlement at grain boundaries by hydrogen-enhanced decohesion mechanism, which is why the fracture surface of the hydrogen-charged sample looks intergranular, has intergranular features at 10% of strain, which is different from the fracture surface of the uncharged sample, which has these ductile features. So this shows that how hydrogen modifies the deformation mechanism and leads to the early embrittlement of material at grain boundaries. So by now it was clear that grain boundaries play a significant role. So for further study, we focused on the grain boundaries also in the recrystallized material, not in deformed samples anymore. But there are two types of grain boundaries observed in this material. So here is the orientation of grains in one grain. And here is the orientation of crystal orientation in second grain. And if the misorientation between these two lie in between 15 to 65 degree, it's a high angle grain boundary in this material. Among these high angle grain boundaries, those which have misorientation angle of 60 degree and rotated around 111 plane, they are twin boundaries. Twin boundaries are those which act as mirror plane between these two grains. And if they have straight structures, such as this one, they are called as coherent twin boundaries. While those which do not have straight structure and are faceted, they are called as incoherent twin boundaries. Now, twin boundaries are specifically important in these materials because when we deform these twip steels, these deformation twills are formed during deformation and they act as obstacles in the dislocation motion, which leads to very high strain hardening and ductility of these materials. So for further study, we first focused on twin boundaries, but not on the deformation twins. We analyzed the annealing twins in the recrystallized material. Secondly, when we performed a thermal desorption spectroscopy analysis, which showed that we really need to heat to very high temperatures in order to dissolve hydrogen out of the material. So this motivated us to perform these experiments on bulk samples without using any cryogenic transfer workflows. So for this, we sent the samples for tritium charging to our collaborators in Karlsruhe. And we sent them bulk samples, which were charged with tritium, and which is a radioactive isotope of hydrogen. And then they were shipped back to Düsseldorf, where we did the lift out and analyzed. So they were not quenched, and there was a time difference of like 4 weeks between the charging and atom probe analysis. And we still observed the segregation of tritium and oxygen at the coherent sigma-3 twin boundary. So, and there was also depletion of manganese. This oxygen segregation was inherently from the material used for the analysis itself, and it got segregated at annealing twins probably during the annealing treatment, because it is also present in the uncharged coherent sigma-3 twin boundary. So here is the coherent sigma-3 twin boundary, which was analyzed from the uncharged material, and it does not have any elemental segregation. So we identified it from the density fluctuations in the 2D ion density map. And it also had the oxygen segregation with manganese depletion. An incoherent sigma-3 twin boundary was also analyzed from the uncharged sample, which has carbon segregation. So it was confirmed by the detector event map, where the inversion of 002 pole, and both of these poles show that it is a boundary in between, which had carbon segregation, but there was no oxygen at this boundary. So this also shows that the grain boundaries with elemental segregation, with carbon segregation, are more resistant towards the oxidation. So in order to conclude, we observed that there is a change in the deformation mechanism due to hydrogen from the formation of dislocation cells to the stacking falls. But in order to really understand the mechanism, we had to find the ways of charging site-specific atom probe specimens with hydrogen, which was really hard and challenging in this case. But when we found the ways, we observed that hydrogen segregation at these grain boundaries leads to the early embrittlement of these materials. And it also shows that not only hydrogen, oxygen is also responsible for the embrittlement of twip steels. And our thermal desorption spectroscopy analysis motivated us to perform these experiments without using any cryogenic transfer workflows. And tritium segregation, which was analyzed without doing the cryogenic transfer workflows, showed that hydrogen analysis by atom probe can be done in this way, but we need to be a bit careful with the analysis conditions, for instance, determining the field evaporation conditions, etc. Thank you very much. And
okay, perfect. So we have plenty of time for questions from the board. Okay, thank you, Hina. So we have plenty of time for questions from the Muller Award Committee. If anybody from the Muller Committee wants to ask questions, please go ahead.
Yeah, I had a question. So really nice talk, Hina. You did a lot of work and a lot of different analyses, so that was very impressive. One question I had was, do you see any potential or expect any potential trajectory aberrations that could impact your segregation measurements or quantifications?
yes, in principle, there are always trajectory aberrations in atom probe, and But in the segregation, more or
specifically?
less, no. I mean, so in this case, if your question is with reference to this profile that I showed here, maybe. Yeah, so in this case, this could be the diffusion profile because the thickness of the grain boundary is like 2 nanometer, but it is also that it is faceted grain boundaries. So in the atom probe, so.
Thank you.
Any other questions from the committee?
Well, Matthias has a question to just exactly this image. Very nice presentation. Doesn't this grain boundary look very wide? And could you say something about that? I would expect usually a grain boundary is much thinner and straighter.
This one is not, this one is faceted. So even in the TKG, I'm not sure if you can still see my.
Yeah, I see.
Yeah, so this one, even in the TKD, it shows this faceted structure. So this grain boundary is not really straight. And yeah, this has faceted and wide structure.
But the reason that it looks so wide is that it is wide, or is it so faceted
It is wide. It is wide.
Yeah.
So it's not really, it is not this wide because of the trajectory aberrations. It is wide. This is what we have observed for some grain boundaries in ECCI also. Maybe this one, if I can show in one of these. Yeah, so here, if there is a boundary, this one, it would look this wide in atom probe for sure, yeah.
But the scale there is like microns, and
yeah,
the atom probe got to nanometers, so it's maybe not necessarily so. Then I have one more about the mass spectrum. Tritium, where do you detect that? And did you see any molecular hydride ions that could be of importance?
No, in tritium, we observed the peak only at 3 in that data set, but also there is carbon in the material. So carbon is detected at 6. So even if there is a tritium-2 molecular ion detected at 6, we cannot really distinguish between the molecular tritium-2 ion and carbon, which is detected at 6. So that is something which I cannot say. Why could we confirm it? Because in this material, in the uncharged, I mean, here is the mass spectrum of the uncharged material where hydrogen is really detected only at 1. So if I charge with deuterium, which is detected at 2, and deuterium was also detected at 4 in my data sets. And if I charge with tritium, which is detected at 3, then we can really confirm that it is tritium. Because in the uncharged sample, there is no peak at 3.
Thank you.
So what about the peak at 19 Dalton? Did you assign it to OT by any chance?
19 I assigned as H3O.
Okay.
But
Yeah.
it is, I think either it is also 3+ state of iron or manganese. I think that is also at 19. That is, one is at 18 and one is at 19. So
if you compare did you compare that with and without tritium data set to see if there is a peak at 19?
Peak at 19 was without tritium also. It is in the uncharged data set. So I think it is one of the, either it is moisture H3O, but I think it is either one of these 3+ charged states of iron plus also. It could be.
Yeah. We have plenty of time. So is there any other questions from the committee?
I have a question about slide 22.
This one, yeah.
Let's see. So here you're showing, actually, I think it's slide 23.
Okay.
So you're comparing this oxygen segregation to the results on slide 21 to show there's no segregation here for those oxygen species. For me, it's just difficult to compare because they're not on the same scale. So if you had plotted this on the scale of slide 21, what would that look like? Would the error bars be similar? To me, you have to kind of squint to see, very low concentrations here with a rising trend.
Yeah, but here the oxygen segregation is like 2 atom%.
So I'm asking, what does that look like on slide 23 with the larger scale? Just 0.2 maybe?
No, okay, yeah, maybe 0.2, but it's also uniform, right? I mean, if the boundary is here, there is no oxygen enrichment at the boundary. I mean, even if it is 0.2 of the oxygen present in the entire material, it's uniform, right?
Okay.
So, I mean, there is oxygen in the material for sure, always. In all of the data sets, there will be a peak at 16 in this material. So there is always oxygen in the material, but I'm comparing its enrichment at the boundaries, that it was not at the incoherent sigma 3, but it was at the coherent sigma 3.
So did you consider calculating an excess measurement for these grain boundaries?
Okay, that I did not calculate, but I'll calculate that. Yeah, thanks.
Yeah, clearly a lot of work went into this.
Thanks.
Yeah, we have some more time, so I can ask one more question. So in your study where you didn't see the dislocations not having segregation, how quickly are you plunged? Like how quickly is the sample frozen after hydrogen charging? And can it be because the lattice trapped hydrogen is also kind of there and everything is kind of high segregation everywhere and you're not able to distinguish what is deeply trapped at dislocations versus in the matrix?
Well, not getting segregation at dislocations has actually several reasons. So one here is the strain rate that I used in my tensile tests. That was 10 to the power minus 3 of the strain rate, which is a little bit higher. So maybe when we are deforming the samples, hydrogen is not following the dislocation cloud, because the deformation is fast and the diffusivity of hydrogen in austenite is slow. So these hydrogen atoms are not able to follow the dislocation cloud. That is one reason. So that's why we do not see it. Second, mostly in this material, we have these screw dislocations which do not have the hydrostatic field where hydrogen likes to sit. So in most of the studies where they have shown the dislocation, the hydrogen segregation at dislocations, mostly they're on edge dislocations, because edge dislocations have this hydrostatic field and hydrogen segregates at them. So that is another reason. Third one, in this case, we simply missed the dislocation cell on the atom probe tip, or also the stacking fault, because I have done the cross-sectional lift out. I mean, I could not do the in-plane lift out for really capturing the stacking fault. So it is possible that I may have missed, because here also the size of these dislocation cells is around somewhere it is 500 nanometers, somewhere it is 1 micron. So but also it might be possible that I may have missed an entire cell, but not a dislocation. So I was expecting that there should be some dislocation in the tip, but there is no segregation. So that simply means that maybe it is segregated at an entire cell, but the cell wall is, if it is broken, then there is no segregation at the dislocation itself. So yeah. There are several reasons for this in this material itself. So yeah.
Okay, great. Does the committee have any other questions?
So for one of the data, you show that basically the tritium was distributed across the entire tape. I'm wondering, what is the charging process? Is this possible, actually this tritium could kept in the interstitial size, or how did you interpret this data?
So this tritium charging was done by the tritium gas charging method so it was a 500 ppm of tritium and hydrogen mixture. And this was a gaseous mixture. So this charging was done at 4 bar of pressure. And it was also done at high temperature, also 70 degrees Celsius for 6 hours. And this grain boundary also has this manganese depletion. So this.
Yeah. So what I mean is in this data set, you basically see tritium was covered in, I mean, you see everywhere. And I'm wondering if the possibility that it's not only grain boundary, instead is the interstitial size or other possibility of such a charging experiment. How did you interpret that?
Yeah, this one you mean at these particular dots. Yeah, this could be also from the sample analysis conditions or sample preparation maybe. But also it can come from the charging, that the charging was not homogeneous. Like there are some defects or interstitial sites, as you say, at these sites where the tritium is segregated, but we could not really find out at what these sites are. I mean, they don't look like dislocations, and this is a recrystallized material in which we do not expect any dislocations. So the grain boundary can be interpreted, but these could also come from the analysis or sample preparation conditions. Or
okay,
okay, perfect. Thank you, Hina. That was very good timing. Now we will move on to next. If you can hang out also for the end time, that will be fantastic. Okay. All right. Next speaker. Thank you. Yeah. Olga, I see you are here. Can you share your slide?
Yes. So I hope you can see my slide and you can hear me.
Yes, we can hear you. Okay, you can start. Thank you.
Okay. So, dear conference member, depending on your time zone, good afternoon or good morning. My name is Olga, and today I would like to present you the work that was made during my PhD project, which was about the nanoscale investigation of austenite-ferrite transformation interface in iron carbon manganese steel at different critical temperature. And this work was supervised by Elena Zapolsky, Frédéric Danois, Mohamed Gonet, and we were working in collaboration with Didier and Nicolas Chardonnay from ArcelorMittal Research Center. And I will start this presentation with a short introduction where I will talk about the general aspect of austenite-to-ferrite phase transformation and the most widely used model for the prediction of ferrite growth. Then I will show you some details of the site-specific sample preparation for interface investigation, and then some experimental result will be presented and compared with the theoretical prediction, and conclusion will be given in the end. And I will start my talk with a very well-known fact that the mechanical properties of the steel are determined by their microstructure, which are mainly tailored by the solid phase transformations that take place during the steel processing. And austenite-ferrite phase transformation has a particular interest for investigation because it is involved in the production line of most modern steel. And this phase transformation is a complex physical process which at least involves two main phenomena. So the first one is a crystal structure rearrangement from FCC austenite to BCC ferrite. And the second is the diffusional redistribution of alloying element. And these two factors can be considered as two main rate controlling factors during the phase transformation. And this phase transformation begins with the preferential growth of allotriomorph ferrite on existing austenite grain boundary, with the further growth that can be treated as one-dimensional planar growth normal to the prior austenite grain boundary. And to describe this phase transformation, many different models have been developed, and the assumption of local equilibrium and para-equilibrium is one of the most widely used. And this assumption belongs to the interfacial transformation models, and therefore they predict the existence of certain compositional profile across the transformation interface that is schematically shown here on the slide. And in the case of local equilibrium with partitioning, the full equilibrium condition assumed to exist on migrating interface reduce the partitioning of substitutional element, manganese in our case, across the transformation interface and into the gamma phase. And in this case, kinetics is expected to be slow since it's mainly controlled by the diffusion of substitutional elements. In the case of local equilibrium with non-partitioning, only the spike of manganese less than nanometer width is expected to be observed at the interface in order to respect the local equilibrium condition. And the transformation in this case will be mainly controlled by the redistribution of interstitial carbon in our case, which means fast kinetics. And finally, in the case of para-equilibrium, it is assumed the substitutional elements are completely immobile with respect to the time scale of transformation. So there is no partitioning of substitutional elements. So flat profile of manganese is expected in this case. And despite the fact that this model was one of the most widely used to predict the phase transformation kinetic, the deviation from this prediction is often reported in the literature. And so therefore, more experimental data are required to support or deny this theory. In any case, we can summarize that the most interesting things during the transformation processing are happening at the transformation interface. And there are many open questions regarding the role of transformation interface during the phase transformation. But this presentation will be mainly concentrated on the interface interaction with the alloying elements, because it is one of the main factors that retards the interface propagation and those affect the transformation kinetic. And one of the main tasks of this study was to get the experimental data of nanoscale solid redistribution at the transformation interface. And atom tomography used in this work is one of the most promising techniques to reach this aim. But in the case of APT investigation of transformation interface, it is necessary to use a site-specific sample preparation procedure. So it will be explained in the following part of my talk. So in this work, we investigated iron carbon model alloy with approximately 0.8 atomic percent of carbon and 2 atomic percent of manganese. And material was treated with respect to intercritical annealing procedure that's schematically shown on the slide, and mainly consists on 3 main steps. So first, austenization, when the material is held at high temperature to obtain a fully austenitic structure. Then it is cooled down to a selected temperature from the 2 alpha plus gamma region below the effectoid temperature and held isothermally for some defined time. And in this stage, the austenite to ferrite phase transformation takes place, and depending on parameter, different mixture of ferrite austenite microstructure will be obtained. And then during the quenching to the room temperature, the remaining austenite transferred to martensite. So in the end, we will obtain the ferrite martensite microstructure. An example of the micrographs you can see on the slide. Here, ferrite is shown in a bright contrast and martensite is dark. And then to localize a certain alpha gamma interface and to obtain the crystallography information, the BSD technique was used in this work. But we have to keep in mind that at room temperature, we are dealing with martensite ferrite microstructure instead of austenite ferrite. And since in low carbon steel, it's very hard to distinguish BCT martensite from BCC ferrite, the image quality map, which you can see on the slide, can be used to provide the better visualization of martensite ferrite microstructure. In any case, it's possible to use the BSD map measured at room temperature to reproduce the original BSD map at high temperature, and using the reconstruction method developed by Ranel German and implemented in Meringue 2 software. And if we will go to the following slide, so using the reconstruction map, the original orientation relationship at alpha gamma interface can be easily determined, but we will not discuss it during this presentation. I just would like to let you know that we have this information. But what is important here is that there are 2 interfaces which were randomly called the first and the second, and we don't know which of this interface is mobile interface of transformation. Or maybe ferrite are going in both directions, so both interfaces are mobile. But in any case, to obtain as much information as we would like, we want to investigate both interfaces. So therefore, the first goal was to prepare the APT tip in the way that will contain both sides of the ferrite grain, as schematically shown on the slide. And the next step was to prepare the set of IPT like that, because first we wanted to increase the successful statistic of the obtained result, but also we were interested if we would obtain a reproducible result along the same ferrite grain, as often we observe different shape and thickness variation along the investigated ferrite grain. And To obtain such set of APT tips, we use a well-known lift out processor. And during this procedure, we are trying to verify the interface propagation down into the material here to have it perpendicular as possible to APT analysis. And then to provide the desired configuration of APT sample, as I presented on previous slide, we were mounting the chunk of the we were mounting the piece of from the retracted chunk on the tip on the side, as you can see here on the slide. And it was a bit challenging part of the sample preparation because of the shadowing effect by FIP welding here. So the first, we did some welding by SEM using the electrons, and then if necessary, we changed the configuration and added welding using FIB. It is a bit tricky part, but as a result, we can obtain the piece of material on the pre-tip that contain both interface as we wanted previously. And then to provide a needle shape to this piece of material with a radius of around 50 nanometer required for APT specimen, we use a well-known procedure of annular milling. But in our case, we have to control the position of the interface from the tip apex. And it is the best if it located less than 100 nanometer from the tip apex. And if you can see on the slide, from the contrast on SEM micrographs, we can easily localize the position of the interfaces at the first step of annular milling. But when tip becomes too thin, we cannot see it anymore. So therefore, to control the interface position, we use TKD technique. That is a transmission version of a BSD. And as you can see on the slide, after several steps of annular milling controlled by TKD, we can localize the first interface on the desired distance. And it's ready to be analyzed by APT, but we will not be able to analyze on the same APT run the second interface, because as you can see here, it is approximately 1 micrometer away from the first one. So therefore, it is necessary to repeat the same, and like first we need to do the first APT run for first interface, stop it, and then to repeat the same annular milling procedure controlled by TKD for the second interface. And this procedure is a bit challenging because there is always a risk of tip fracture during any step of manipulation, but the obtained result worth it. So, and if both APT runs are successful, we can obtain following result. So as you can see on this slide, so 3D reconstruction of carbon and manganese atom for both volume with both interface. And we could plot the compositional profile perpendicular to the interface. And here it's important to say that even if you have a profile for both carbon and manganese, in this study, we will mainly focus on the interpretation of manganese segregation, since the original of carbon segregation in our case is questionable due to its high diffusivity even at room temperature. But carbon composition change from the carbon-rich martensite to pure carbon ferrite zone. It's one of the simplest way to identify the transformation interface, especially during the first APT acquisition when we need to stop this run by ourselves. But on the next slide, I will only show you information related to manganese. And the first information that can be extracted is the value of maximum of manganese peak and the average composition in martensite, pyrostenite, and ferrite site. So, but if you will have a look on another example where the composition profile shown for the first three tip across the first interface, we can see how the orientation of the measured interface with respect to the analysis of the APT axis affects the height and the width of measured peak. So this presented result, a very nice example why we cannot use the peak value as a quantitative measure of segregation. And in addition to the observed issue, APT&M measurements can be also underestimated due to well-known local magnification effect. So therefore, to quantify the manganese segregation at the interface, it is necessary to calculate the interfacial segregation known as Gibson interfacial access, because it's independent on experimental condition. So Gibson excess is a number of accumulated atoms at the interface divided by the interfacial area. And as APT technique derives a discrete count of atoms in analyzed volume, it was proposed by Hellman and Simon to calculate manganese excess using the integral profile that you schematically see on the slide. However, this method requires the definition of the position of the plane interface that supposed strictly separate two phases, austenite and ferrite in our case. And this plane is called dividing surface. And when we have the symmetrical profile, so when the atomic fraction of solid atom in both phases are identical, it is not a problem because, as you can see from the following animation, doesn't matter where we place this Gibbs dividing surface, the value of manganese excess doesn't change. But it is not a case when the composition are not equal in the both sides, which is exactly the case of the present work. So from the next animation, you can see that the position of dividing surface influences the excess value. So the question here is how to choose this position. Logically, we can place it at the peak of the composition profile, but there is no strong argument that this is the correct choice. And for the moment, there is no unique solution in the literature how to define the position of dividing surface in the case of the heterogeneity system. So therefore, we decided to do some estimation how the manganese value is affected by manganese excess value is affected by the mispositioning of dividing surface within of manganese peak within a few nanometers, because it was approximately observed width of manganese peak experimentally. And for that, we plotted several testing profile with different composition on both sides, as you can see the value here. And this difference was chosen with respect to the experimentally observed one. And I would like to highlight here that in 90% of our cases, we had this situation. So it means that less than half of atomic difference and the estimation shows that it's not, as you can see from this graph, that the estimation shows that it's not significant different. So therefore, in our experimental data, we calculate manganese excess by placing the dividing surface at the peak, but we provide the manganese excess with the deviation which correspond to ±1 nanometer for dividing surface displacement. And now I would like to show you some APT result. And in the case of transformation temperature 625 Celsius degree. And if you will have a look on the isothermal phase diagram at this temperature for the alloy with the investigated nominal composition shown here in as a red point, we expect that LNP or para-equilibrium is operating during at this temperature. So just to remind you that in the case of LNP, we expect manganese spike less than 1 nanometer width, and in the case of para-equilibrium, manganese profile expected to be flat. So in this transformation temperature, we obtain approximately 40 successful results. But since we observe a similar shape of manganese profile for the most of these results, there is no reason to show you many similar profiles. So on the next slide, I will show you just an example of the observed manganese profile at this condition. So on the slide, you can see the 3D reconstruction and compositional profile across the both first and second interface of tip 4 shown here. And the first that we can say about this result, that we can without any doubt reject the para-equilibrium assumption in this case, because instead of flat profile of manganese through the interface, we clearly observe manganese segregation and both interface, which can also mean that both interfaces are mobile. But now the question, if the observed manganese peak can be treated as manganese spike. Of course, the experimentally observed width is significantly bigger than the expected one for the manganese spike, but the measured peak width by APT always can be argued by the spatial resolution, so we cannot compare this parameter. However, there is another point that can be highlighted, it is clear observes the manganese composition different in ferrite and martensite, pyrostenite, and it's just not expected under the LNP condition because the compositional profile on the both sides from the interface is supposed to be equal. So it is already a strong argument to say that the observed experimentally manganese peak cannot be treated as LNP spike. But to have additional argument, we compare the experimentally measured data with the calculating using the Dichter model of thermocalc software. So on the slide, you can see the initial configuration and the result of calculation for 5 seconds and 30 seconds. And we obtained manganese spike with the maximum that defined by the phase diagram. And the spike width extremely small, approximately 0.04 nanometer. And to compare this data with the experimental one, we calculated manganese excess as the area under the peak. And if we compare it with the experimental data, so first of all, we see that the calculated manganese excess, here is this green point, is not evolving with time, at least at the early beginning of the transformation, which is not the case from the experimental measurement. But what is more important is that it is almost several orders of magnitude different. The manganese excess value is really order of magnitude different compared with the experimentally measured one. So, sorry. So based on this data, we can conclude that LNP cannot be used to describe the observed manganese profile at 625. So therefore, we have to find another model that will better describe the experimentally observed result. And recently, the solid drug-based model started to take more and more attention. And based on the description of the interaction of solid atoms with the moving transformation interface through the phenomenon known as solid drug. And one of the main assumptions of solid drug-based model is that the transformation interface is considered as a particular phase with a certain thermodynamic and geometrical properties. So, and then to describe the evolution of the compositional profile, the diffusion equation has to be solved for each of these zones, for austenite, interface, and ferrite. And to solve this equation, it's necessary to satisfy the McLean equation and mass balance equation. And on next slide, I would like to show you some result of the calculation using solid drug-based model at 625 Celsius degree. And in this video, you can see directly the evolution of the manganese profile with time and the evolution of the average velocity of interface that was determined from the dilatometer data. And also you could see the position of the interface within time. And if we just compare the predicted profile for the different transformation time, for the short transformation time and long transformation time, we can see that schematically the predicted profile by solid drug very much better describes the observed experimentally. And if we compare quantitatively the amount of manganese segregation measured experimentally with the result obtained using solid drug-based model, we can see that it provides a more convincing comparison than with the result obtained from Dichter. I just would like to mention that on this slide, I show you the comparison in the case of 680 Celsius degree of transformation temperature instead of 625. As this temperature, we had more data, so we can provide better statistic for comparison. But I assure you that we observe a similar tendency also in the case of 625. So first of all, from this graph, we see the tendency of manganese excess to increase with time, which is clearly observed experimentally and also predicted by solid drug model. And of course, take into account a significant scatter in experimental data. For the moment, it is a bit difficult to define appropriate parameter for a solid drug model in order to provide the accurate quantitative description of austenite to ferrite phase transformation. But based on the presented result, we see that solid drug provide much way better qualitative description of the experimentally observed profile at investigated condition. And so then the model used the assumption of local equilibrium. So therefore, the solid drug-based model are very perspective direction for the description of austenite to ferrite phase transformation that was brought thanks to the unique data obtained by atom probe. So, and I would like to conclude that thanks to atom probe technique, we obtain unique data, and also we develop a new methodology that for interface analysis, we significantly increase the successful number of the successful run. So more than 100 interface was successfully analyzed. And this APT data help to determine that the solid drug is operating mode during the ferrite growth and investigated condition. And but what is more important is the further APT investigation in this field can provide a very important parameter for the development of solid drug-based model, which are very perspective. Thank you for your attention and ready for your question.
Perfect. Great timing. Thank you, Olga. So if the Muller Award Committee wants to ask questions, you have time now. Go ahead.
All right, may I start, Matthias here? Thank you for a very nice presentation and very fundamental work. I have a question regarding the difference in manganese between the martensite and the ferrite. Was that confirmed by other techniques? I guess it should be enough to see it also with EDX?
For the moment, no. Of course, we try to do some EDS, but the resolution is not enough. We don't see a difference. So we see it very clear only by APT, but it's also predicted by solid drug model. So this theory also predicts a different composition. But we expect that because there is some plan to do some TM, so we expect to observe the same.
Thank you. I mean, could you think of any reason that the manganese difference from atom probe could be wrong?
Not really. Not really, because it has quite a close evaporation rate to iron, which is a matrix. Of course, there could be question about the how at the interface, because of course there can be some aberrations, some local magnification effect. But there is also the segregation of carbon and segregation of manganese, so we expect that it will compensate a bit. So we expect that observed data represent very well the situation.
And this was voltage pulsed at 50 Kelvin, is that correct?
Yeah, yes.
Great. Another question. Now you looked at the model system. What was the main reason for that? I mean, I could be very interested in seeing a silicon profile or something like that, but you choose to take a model alloy. Could you comment anything on that?
Because like the goal first was, so there is a big theoretical part which are made by our industrial partners. So they want to develop some model which they can use to predict the austenite to ferrite phase transformation. And so the goal was just to obtain as much as we can statistic data by atom probe that they can use it to confirm their model. And of course, for the moment, this model is successful only for 2-component system. So it's even more far from the 3-component system. And of course, it could be some coupled solid drug effect, and it's very complicated. So they wanted like simple model alloy have to make easier the comparison with their theories that they develop.
Right. Thank you. I hand over to someone else.
Thank you.
Okay. Anybody else?
Hey, Olga. I had a question or two. Nice presentation. I had a question about your solute drag models, where in slides 21 and 22, you showed these results of how the models are predicting qualitatively similar manganese profiles. But you mentioned that quantitatively, the descriptions don't quite match. And so I was wondering what additional information or what it would take to get the models to match with the APT data.
So indeed, so one of the main parameters that used in this solute drag-based model is the binding energy, the interface thickness. So we try, and we see that if we check different interface thickness, it affects the quantitative result. But as I already mentioned during my presentation, that the thickness of the measured APT peak can be argued by the spatial resolution. So it is quite challenging to be sure about the exact number. But what is very important that we can define the binding energy. For using knowing the amount of the segregation, we define the binding energy. So we already have one parameter that can be used in the modeling, and we successfully did that.
Okay, thanks for describing those factors. One other question I had, if I have time, is you mentioned that future work you're interested in doing TEM measurements or experiments with these type of samples. And maybe it's more of a comment, but I was curious as to whether you were considering doing like in situ TEM experiments where you're heating the specimen to see how the boundary is migrating.
So what is very important for us regarding TEM is just to try to verify the thickness of the interface. But now, after it will be the question about which thickness we are talking about, crystallographical or about chemical one, because the thickness could be different. But what is important for us is in situ TM, or it could be in situ EBSD, and maybe now we are even more for in situ EBSD investigation, because the actual interface velocity is very important for us, because as we see from our data, as I mentioned, more than 100 interface was successfully analyzed. And we see different shape of profile, and we expect that it's affected by different kinetic. And even more, I did not discuss the point of orientation relationship, but we very clearly see the effect of orientation relationship on the profile. In one case, we expect that it's faster, and another one it's slower. So in situ EBSD, it will really help us to, so because now when we are looking on profile obtained by atom probe, I could say that, okay, I almost sure that this interface is more mobile and this one is less mobile, only looking on the compositional profile. But we need to verify it by knowing not only by our guess, but the fact. So we need to measure the actual interface velocity. But we are also now into it. So hopefully soon we will have some nice result.
Yeah, that would be a nice combined study to have the EBSD to look at all the different orientations, and then maybe with TEM just look at some specific orientations that seem to be of interest. So very cool. Thank you.
Okay, fantastic.
Thank you.
Thank you all. So please stay as other speakers up to the end of the final talk. All right, Martin, are you here? All right. I cannot hear you still.
I'm here, and I was busy with sharing my screen. Sorry about that.
No problem.
Yep,
okay.
Ready?
All right. Yes, you can start now.
Okay. Well, thank you very much for coming, everyone. Thanks for listening to my talk. My name is Martin. I'm a fourth-year PhD student from the Oxford Atom Probe group, and I directly propose that you all ignore this title and the first slide, because I brought you something that's way cooler. Look at this. We analyzed the field dependence of contaminant hydrogen. You won't believe what amazing phenomenon we discovered. Let's go. We shall start with a quick introduction into hydrogen. So you will all probably be fairly familiar with it, and many of you will even see it every day. So it's a characteristic contaminant that is turning up with a hydrogen 2+ peak at a mass charge ratio of 1, and a characteristic second peak with a mass charge ratio of 2 for the hydrogen 2+ ion. And whilst this looks fairly simple, it's actually a surprisingly complex phenomenon. And it depends on pretty much all of the parameters that we have at our disposal in APT. So there are dependencies on the voltage or the electric field, the laser if you're using it, the pulse frequency, the material, and that's especially a problem if you have a strong hydride form like zirconium, and probably even many more parameters that we so far have not even discovered yet, or that we do not have control over. And that's a major problem if you want to do hydrogen imaging, because when you see hydrogen, you can never really be sure, are we looking at a contaminant signal, or is it real sample hydrogen that we get in our data set? Therefore, we need to understand this contaminant better. So basically, we need to know where it comes from, where does it go, and therefore we have done more research. The first idea that we have is the following. Every atom probe experiment contains hydrogen, and that means basically as a byproduct of every APT experiment that we run, we also investigating the contaminant hydrogen at the particular parameters of this experiment. So we thought about this. Can we actually just go back into our archives and dig up old data sets and see if there is statistically anything relevant that's in there about the contaminant hydrogen signal? Now, when you want to do that, there's actually a problem that you run into fairly quickly. And this is that the atom probes, the machines, they do not give us nice reconstructions, and they do also not give us nice spectra. All that they give us is raw detector signals. And then we need a specialized software like IVAS or like AP Suite in order to extract spectra and other results out of these. There's no direct and straightforward way to do this quickly for many experiments, but we have found a workaround, which is user interface automation. So what we have is, we have a script that's running on a computer, and it's triggering mouse clicks and keyboard inputs into IVAS to just load a raw detector file and export all of the data that is in there. So this is what you see here. The script is starting on the computer, and this in turn is starting IVAS. And now there is a big red mouse pointer running around on the screen really quick, and it's loading the detector files. It's walking through the IVAS reconstruction wizard, and then it's saving the files for us. And this is something that goes fully automatic and that we can run all day and all night. And if you run for long enough, we will eventually end up with a really big pile of APT spectra. And now we can search for hydrogen in there. The next two steps that we do into these data sets is, firstly, we identify the material. And once we know the materials, or at least once we know the main ions in there, we can calculate charge state ratios and electric fields. In addition to that, we can also calculate the hydrogen peak height ratio. So the counts of the H2+ ion divided by the counts of the H+ ion. And what this is doing is essentially it is condensing at least a good measure or a good approximation for what the hydrogen spectrum looks like in a particular experiment into one single number that we can easily track across many experiments. And now this is everything that the computer needs in order to work out what hydrogen is doing in APT. So computer, what do you know about contaminant hydrogen in APT? Hello, I'm the computer, and everything that I know about contaminant hydrogen in APT is condensed as this single diagram here. What am I looking at? In order to get to this diagram, we've done the following. We take a large number of APT experiments, all of them in laser mode, and we slice them along the voltage axis. Then for every experiment and every voltage slice, we calculate the hydrogen ratio and we calculate the electric field, and we add a dot into this diagram. So what you're seeing here is the behavior of the contaminant hydrogen signal across many experiments, across different materials as function of the electric field. Cool. So how would you interpret this data then? It seems like there are two regimes to this diagram. Firstly, there is this low field regime, which goes up to about 25 volts per nanometer. And what we see is that as the electric field increases, the hydrogen ratio decreases. My spontaneous guess is that this is down to post-ionization. So we might be evaporating hydrogen 2+ out of our tips, but this might then post-ionize and dissociate into 2H+. And this could explain why we're seeing a decreasing ratio, which corresponds to that shift away from hydrogen 2+ towards a hydrogen plus peak. But then there is also this high regime area here, which we see above 25 volts per nanometer. And that's coming in a bit surprising because we see that in this region, the hydrogen ratio, it appears independent on the electric field. In particular, we see that this is not saturating at 0, but a value slightly above that. And what this is essentially telling us is that the hydrogen 2+ peak, it never goes away in laser mode APT. Even at very high electric fields, all of these experiments, they contain a H2+ peak. Yeah, well, but why is that? Well, where does it come from? Where does it go? I don't know. But you're the scientist here supposed to work it out. Well, thank you for that, computer. We're going to come back to you later, maybe. So we have just learned that there's possibly something interesting happening in hydrogen in laser mode experiments at high electric fields. So what we do is we do a couple of experiments just to confirm and to see what might be going on there. We run tungsten tips because tungsten is naturally a high field material, so we can easily get APT runs at high electric fields out of these. And what you see here is the contaminant hydrogen spectrum in a tungsten tip that was run in laser mode on a reflector machine. And indeed, both of the hydrogen peaks are here. So far, this is in agreement with our observations on archive data. But it's also not really interesting, is it? There's something more interesting that we could do, and this is repeat that entire thing on a straight flight path machine. And what we see in this experiment is that the H+ peak is turning into a split peak. So there is now one part of the peak that is just at the mass charge ratio where we expected, and a second relatively large part that we detected an unusually high mass charge ratio. And this is down to an energy deficit. So it appears that a good amount of the H2+ under these conditions, it's flying slower into the detector than we would usually expect it to. What we do in these combos is we call the first peak a peak and the second peak we call a hump. So there is no such thing around like a proper scientific nomenclature that's established there. So peak and hump, these are just the words that we use in this presentation. So we have something to talk about. And then let's check the mass charge 2 peak. And what we find is there is no peak at all. There is only a hump. So all of a H2+ that we see in these experiments, it's evaporating with an energy deficit. A third experiment that we can then stack on top of this is another repetition of that entire thing, but this time on a deuterated tip in a straight flight path machine. And deuterium is a hydrogen isotope that's naturally very rare, and that's twice as heavy as the naturally abundant light hydrogen. And what we see in here is this. The mass charge 2 peak, it is now back, and that's because of deuterium. So, and what this is telling us is this. The fundamental field evaporation of hydrogen or deuterium out of our sample, it has not changed. The deuterium from the sample, we are still evaporating and detecting it precisely with the energies and time of flights that we would expect. The energy deficit, it seems to be something that is exclusive to the contaminant hydrogen signal. And now all of this leads to the big question, so what? We now are 100% certain that there's something really fishy about hydrogen that we see in laser mode high fields. Well, because firstly, it seems to never go away, the H2+ peak. There is this constant peak head ratio. And now we also know that there's an energy deficit involved somehow. The only question is, what shall we do next? And what experiment could we do in order to dig deeper and really find out what is going on these tips? We came to the conclusion that the tungsten experiments that we have run so far, they were probably insufficient by quite a lot. Because of this, the tungsten tips, they naturally run at a very high electric field. And as such, they can only confirm these observations that we make about the odd type of hydrogen at high fields in our archival data. But what we actually want, and what would be way more interesting, is a series of hydrogen spectra that we record at different electric field strength. And then we could really see, well, when is that transitioning from what we would call the normal behavior into this unusual behavior happening? What is triggering it? And what else could be relevant parameters here? So what we want to do is we want to control the electric field at which our tip is running. The common way of doing that is changing the laser power, because if you have a higher laser energy per pulse, then your tips, they usually run at lower electric fields. But for our experiments, we thought there's actually something smarter we can do. We could run APT experiments below the evaporation threshold. And that sounds silly, but it actually makes completely sense. Think about this. Contaminant hydrogen, it's arriving at our tips whilst the experiment is running. And this means even if the electric field is so low that there is no tungsten coming out of our tip, there's still a potential for contaminant hydrogen to arrive at our tip, to evaporate and get detected. And this means up to the evaporation threshold of tungsten, we can actually very precisely navigate to any electric field and see what the hydrogen spectrum is doing in there. Here is how these experiments work in the lab. So what you see here is a voltage curve of an APT experiment with the IN sequence on the x-axis and the voltage on the y-axis. And we start the APT run with an electropolished tungsten tip. The voltage increases quickly, and eventually the evaporation kicks in, the tip turns on, and the voltage ramps up a bit more slowly. Once we get a nice run, we stop the auto voltage control algorithm, and this causes the voltage to go constant. And then we come in and we manually decrease the voltage until the evaporation of tungsten completely stops. And we know the point of time when the evaporation has stopped by just looking at the spectrum. And once there are no tungsten peaks left, then we know, well, there's nothing evaporating out of the tip anymore. But we do still see hydrogen peaks. So that means we can just let the sample sit at an electric field and accumulate a spectrum of contaminant hydrogen. And once we are happy with the spectrum we've had, we just continue to another voltage, record the hydrogen spectrum at a different electric field strength, and so on, and collect our series of hydrogen spectra at different electric fields. In particular, what we can then also do is repeat that entire experiment many times again with different parameters, like in laser mode and voltage mode, at different laser energies with different pulsing frequencies, and so on. All of this on one tip that never evaporates and that never changes geometry. And what this does is it gives us a set of very well matched and paired hydrogen spectra where we can really see what the relevant parameters are and what might possibly be going on in our tip. Now, before I show you our results, a quick comment about the electric field. Usually, we calculate an electric field in APT by using charge-state ratio, but that's not going to work if there is no tungsten evaporating because there's just nothing that we can use for our CSR. We use a quick workaround. What we do is we actually do know the tungsten CSR just at a point in time where the sample stops evaporating. And we also do know that given a constant tip radius and given a constant geometry, the field is actually just proportional to the voltage. And this allows us to calculate the electric field and any voltage below the evaporation threshold just through a linear interpolation. And all we need to do is make sure that we never accidentally change anything at the geometry of our sample. And now with this, time for some results. What you see here is the relative ionic fraction of hydrogen 2+ to the sum of both hydrogen peaks. So essentially, that's a peak height ratio on the y-axis as plotted against the standing electric field in 3 laser mode experiments. The 3 experiments, you see it in the legend, 200 kilohertz 2 picojoule laser mode. Second one is 1 megahertz, so 5 times as many pulses per time. And the last one is 10 picojoule, so 5 times as much energy per pulse. And you immediately see that these 3 lines, they overlay pretty much perfectly. And this is telling us that within the range we've tested, the pulse frequency or the laser energy, it has basically 0 influence on the appearance of our hydrogen peaks. The relevant parameter that we need to keep an eye on, it really very much is the standing electric field, which we have on the x-axis in the diagram here. Now, when we go through it in a bit more detail, the first data point that you see in here is a gray X, and that's the symbol that we use for an empty spectrum. So if the electric field is too low, there's just nothing evaporating at all, and that's why we are making these observations here. But then if we just go a bit higher and evaporation starts, we see a spectrum, and that's as expected, dominated by the H2+ peak. And as the voltage increases, that eventually turns around, the H1+ peaks over, but as we go to very high electric fields, the hydrogen 2+ peak does never disappear, and the peak height ratio, it appears constant between the H+ and the hydrogen 2+ peak. And that's an observation that made us very happy, because that means that we have just reproduced observation that we make on our archive data sets. And now that we know we can reproduce this, we can actually come back even many more times, make variants of the experiments to figure out what's going on. Now, the 2 next slides, they have two more observations that are relevant. And I'm afraid it's getting a bit tricky now. So full concentration. First, we repeat that entire thing in voltage mode, still on the same tips. And there's two important observations that we make in here. Number 1, in voltage mode at high electric fields, the peak height ratio, it goes straight to 0. And that is corresponding to a spectrum without a mass charge 2p. And this is really something that so far we have not seen in any of the laser mode experiments. Secondly, in voltage mode, if the electric field is high enough, the spectrum becomes empty again. And it is also something that appears to be exclusive to the voltage mode experiments that we do here. Now, there's two possible ways in which we could interpret this empty spectrum in voltage mode. A, in voltage mode, given a sufficiently high electric field, there is no contaminant hydrogen left at the tip. Or B, in voltage mode, given a sufficiently high electric field, there is contaminant hydrogen left at the tip, but it all is evaporating off pulse such that we don't detect it in our time of flight spectroscopy. And depending on which of these two interpretations you believe, there are also conclusions that we need to draw for our laser experiment. So number one, the laser is doing something to the experiment that is causing a supply of contaminant hydrogen onto our tip, even under conditions where there's no contaminant hydrogen in the tip in voltage mode. Or number two, the laser is doing something to the experiment that is causing the on-pulse evaporation of contaminant hydrogen, even under conditions where all of the evaporation is happening off-pulse in voltage mode. The second observation that we can make is concerning the peak shape. And what we find is the following. On this falling slope of the diagram, so this part where the hydrogen has the behavior of what we would call the normal behavior, the peak shapes, they're also the very normal peak shapes that we usually see. So what you see here is the mass charge 2 peak closely zoomed in, and we confirm this is a peak, this is what a peak looks like, and so far so boring. But as we go to higher electric fields, this is changing. When we get into this field independent region here, we see that first the peak gets this oddly wide shape, and eventually it is turning into this, and this is what we previously called a hump. This is now an energy deficit that we're observing here, and we find that it is the energy deficit type of hydrogen that is causing all of these odd observations that we make in laser mode at high electric fields. And now that we have made all of these observations and that we have approximately an image of what's going on, we can try to speculate a bit what might actually be going on the tip on a molecular level. Now, the problem, of course, with these things is this: it's very difficult to completely prove or disprove any of the mechanisms that have been proposed or that we might propose. So we are also not 100% sure about this. The literature is full of theories that are difficult to prove. So where does it come from? Where does it go? Maybe we won't ever know. But if you have a good idea, or if you think I'm completely right or completely wrong, then do make sure to send me an email. Here is what I think is going on. Number one, I believe what we're seeing in this low field regime is an incarnation of post-ionization. So the way it would work is this. We have a hydrogen 2 that's adsorbed in our tip, and it's field evaporating, and eventually it's post-ionizing. Now, if you think about it, the hydrogen 2 molecule, so this thing here, it is only 2 protons and 2 electrons. So after post-ionization, there are both of the electrons are gone, and there are just 2 protons are left. So there's nothing that could possibly hold this molecule together anymore, and it must immediately dissociate. Sorry. Post-ionization is more likely if the electric field is high. And this could explain why we're seeing this field-dependent shift away from the hydrogen 2 plus towards the hydrogen plus. One thing in there that's also giving me a bit more confidence when I make this claim are the correlative diagrams. So what you see here are 2 correlative diagrams that we have extracted on the falling slope of the diagram, 16.6 and 22.5 volts per nanometer. And indeed, we see there are quite strong 1-1 events. So H plus followed by another H plus within the same laser pulse. There are way less 1-2 events or 2-2 events in there. And thirdly, there are also other authors who have written similar things or who have done different experiments and come to compatible conclusions. There are 2 references on the bottom left, and there is more in the literature. So what we might have here is might actually be a fairly credible explanation for what is going on at these low electric fields. But then, of course, the way more interesting question is what is happening at high electric fields? I thought for quite a while that we might be running a residual gas film. So basically, in parallel to all of our APT experiments, we are running a field ion microscope on the residual gas. The way it would work is this. We have a contaminant hydrogen in the gas atmosphere. It's getting attracted to the tip, polarized by the electric field, and attracted by the electric field. It's eventually bouncing around a bit, and then it's finally ionizing and flying into the detector. Now, the ionization in field ion microscopy, it's commonly believed to occur through a tunneling effect away from the surface. And this ionization away from the surface, it could possibly explain why we're seeing an energy deficit in there. However, after thinking about it for a bit longer, I actually came to the conclusion maybe that's not a good theory here, or at least not a good explanation. Because what we know is that the laser, it is essentially just adding temperature pulses to the tip. I do not really see how a temperature spike in a tip could trigger a tunneling effect of an ion that will ionize a molecule ahead of the tip. And I think that's a major problem, and it probably means that residual gas film can't explain what we're seeing here. There is a second possibility that's also that has been discussed in the literature, and this is that the laser could cause neutral desorption of hydrogen-2 from our tip. This will then fly away. Eventually, if it will ionize at a critical distance and then fly into the detector. Once more, we have that advantage of the away from surface ionization, which could possibly explain an energy deficit. But there's also a problem with this theory. In voltage mode, we have seen that at high electric fields, A, there is no hydrogen left at the tip, or B, all of the hydrogen is evaporating off pulse. So the question is this: how, in the first place, how would it be possible for a H2 to sit on this tip here on laser mode, and why does this not immediately fly away in the standing field? It would still be possible that maybe the laser is also doing something to supply a lot of hydrogen onto the tip, but it definitely is a bit of a point of concern. It's raising a major question mark above the model, and it's something that we would need to explain first if we would believe that this is what's going on in the tip. We thought about the following. Now, the fact that we are observing hydrogen in a laser mode, which we do not observe in voltage mode, it almost begs for an interpretation that there's somehow involving something happening outside the field of view on a tip shank. So maybe the laser appears to have some interaction with the sample body that is triggering all of this extra hydrogen. Could it possibly be something like this? The laser is triggering a neutral desorption on a tip shaft outside the field of view. The released hydrogen is turning into imaging gas really very quickly for a very brief amount of time. And this may really be just in the region of nanometers, this flight path here, until it eventually ionizes ahead of the tip and flies into the detector. It's something that we can't prove and we can't disprove, but so far it seems something like the best fit to what we are seeing. At least we have not had any better ideas. Make sure to email me if you got one. Now, before we go to the grand finale, a quick recap of what we have just seen. If we have a big pile of past experiments, then you have something that's extremely useful, because when there are observations that we can make statistically across many APT experiments, they will be in there and we can dig them up. What we do is we focus on contaminant hydrogen, and we find that indeed there is something interesting and it appears to happen in laser mode at high electric fields. So this is leading us to our experiments where we run these tungsten tips, and we find, yeah, there is something, and it seems to involve an energy deficit. On top of these experiments, we can then stack these runs below the evaporation threshold. And what they do is they give us a very clear image of which parameters are influencing the hydrogen behavior and how, and we can then start speculating what might actually happen on a molecular level on this tip. Now, finally, there's actually one more really big win that we can collect. And if you're familiar with hydrogen imaging in APT, maybe you've already spotted it, maybe you already know what might be coming now. We briefly return to the introduction. I said imaging of hydrogen is difficult because we never can be sure if the hydrogen is coming out of the sample or if it's actually, or if it's just a contaminant signal. And the common workaround that is used in the literature, it is this: we use a deuterated sample, and then we fiddle around with the parameters until we get a spectrum that looks like this. So separate peaks for contaminant hydrogen plus and deuterium plus that's coming from the sample. But this is not working if your sample just decides to evaporate dimer molecules, the hydrogen 2 plus, because then in your spectrum, you will get this overlap of contaminant H2 plus and sample deuterium, and there's no way you can work out what is coming out of the sample well and what's contaminant. This is no longer strictly true. We have shown that if you get the parameters right, you can totally produce an energy deficit in contaminant hydrogen, which means you can now tell apart the hydrogen, the deuterium from the sample and the contaminant hydrogen. And what this does is it's enabling hydrogen imaging in laser mode. So what you see here is what I claim to be the first successful direct imaging of deuterium in laser mode APT, without with the full resolution, with the full sensitivity, without the need for any further tricks like peak decomposition. What you see, by the way, that's an implanted deuterium sample. So the deuterium is following a depth profile. There's an implantation front. Not a lot of deuterium here, but then it's a radiation damaged sample, so there are trapping sites where it's staying here. With these pictures, thank you very much. Thank you for staying up late. Thank you for getting up early. Thank you for coming. And the computer is now going to take your questions.
All right.
That's right.
Perfect. Thank you, Martin. All right. So is the Muller Award Committee here? Okay. All right. A question from you guys.
I can start off. Thank you for your presentation. It was quite a body of work you have there. So a question and a comment. So the data that you mined, I'm guessing that most of it was taken at a constant detection rate over time. Now, sometimes what we see here is, an increase in DC evaporation as your tip gets larger and larger over time. So I'm wondering, how you've dealt with any implications of that in your data mining work.
So what is actually in there is, I said we are slicing them along the voltage axis, and actually on every voltage slice, there is a background correction. And we are assuming a time of flight constant background. So I hope it's working well. I guess the problem is when if there are experiments where there are really few counts, then this is not going to chop off the background well. I'm not 100% sure if I might actually have rejected data points where the counts were just too bad, but there is actually a background correction in there.
Okay. And then just a comment, the LEAP 5000 and beyond has the ability to run at constant charge states and, constant detector flux. So I think this would be an interesting application of some of these advanced acquisition features to, look at this hydrogen ratio background over time.
Oh yeah, that was a constant CSR run that you've seen in the tungsten experiments. So on that slide, we are running at above 35 volts per nanometer, and that is approximately equating to a 50-50 ratio of the tungsten 3+ and the 2+ ion, and that's something that that actually works fairly well.
Okay, thank you.
I have a question. I think with the experiment you did was a laser run, you have a tungsten tip and you didn't let the tungsten to evaporate, and it's very neat. And I'm wondering, like, you play around with the laser energy, like the 2 picojoules, 10 picojoules, and a little bit pulse frequency. I mean, essentially, you talk about if you don't let tungsten evaporate and the laser energy would not play a role, it's basically hydrogen, it just like it's working like mechanism of the fin. And in this case, why did you choose different laser energy to compare this ratio? Then, I mean, that is kind of, we expect it will be the same, right? Because it's essentially a similar field.
Yeah, precisely. This is what so I'm afraid I might have not gotten the second part of your question. But yeah, what this diagram is really showing that it's confirming that the laser energy does not have an influence on our hydrogen spectrum. There's actually one thing that I maybe would add. What these experiments do below evaporation threshold, since we are not evaporating any sample material, we are also automatically switching off any effect that we might have from complex molecule ions, like zirconium hydrides or so, which are fairly common, which would also affect the hydrogen spectrum, because if these molecules that dissociate, then they will add more hydrogen to the hydrogen spectrum according to their very own rules. I sort of, I'm not sure, but I could very well imagine that such complex hydride molecules, they're influenced by the laser energy, and therefore we could get in some materials and some runs an indirect influence on the laser energy. But yeah, for just our plain tungsten tips that are not evaporating, this is indeed well, very much confirmed that the laser is doing nothing.
Can you please elaborate why you use a different pulse frequency to see the ratio and why you choose so?
Yeah, well, the thing is this, what we wanted to work out is the hydrogen actually time constant or pulse constant. So the thing is, we know that the hydrogen is arriving in our tip whilst the experiment is running, and we were interested, is actually the supply per time constant, or is the supply per pulse constant? Because then we're using 5 times the pulse energy. For example, because the laser would be driving some sort of diffusion of the tip shank, then you would actually see a dependency on the pulse frequency.
I have another question.
Yep.
So if the hydrogen peak ratio, is dependent on field. Do you think we could do the reverse and use this peak ratio as an estimate of field for any specimen type?
Well, so I'm not sure. The thing is, since I've seen these experiments of mine, every time I look at a high tungsten spectrum, I try to estimate what field they're running at. I'm not quite sure how accurate it is. I could imagine if you really manage to reproduce your samples very well, such that there is nothing going on with the peak with the geometry also, and if you can rule out that there's anything happening to complex hydrides also, then it might be possible. But I believe it's fairly limited. So the CSR definitely is the way to go if you want electric field.
I'm wondering, like you were talking about this zirconium H complex molecules, and for such a say hydrogen zirconium, and there's also curiosity like this is really zirconium hydrogen was initially bonded in materials, or is like what you said is basically the association and recombination with zirconium hydrogen, and you think you can use this energy deficit to distinguish this effect?
Sorry, I think your sound quality on my side is quite low.
I know it's So what I mean is about zirconium H peak. Do you feel like this is really from the material is zirconium bonded as hydrogen, or this is something you can differentiate from the energy deficit? In fact, there's something recombination process during evaporation.
So I think my opinion about this has changed after I've seen a talk at APT&M conference, because I forgot his name is, but somebody from Florent who had an invited talk where they showed that there's a remarkable behavior of contaminant hydrogen and aluminum, and it seems that this hydrogen is, if I get it right, I think it was the hydrogen is leading to a lower evaporation field. So basically the molecule ion is evaporating more easily than the actual material. And this means if this is a thing, then it would also mean that basically the hydrogen that's on our surface and is not part of the material, it may very easily react with the material simply because it has a lower evaporation field. And I think I've seen once in some old literature where somebody wrote that a hydrogen that's actually standing upright on a surface molecule, it might almost act as something like a lens, because it is something that's protruding. And I think, therefore, it would be very difficult to tell a difference between a complex hydride that's coming out of the sample and a complex hydride that's forming on the surface, because it's probably this phenomenon might actually be too dynamic. So there might indeed be too much recombination and dissociation going on between from the material and the sample until it's actually ending up in a detector.
All right. Thank you, computer or Martin, I don't know. Thank you.
Well, thank you, and thank you.
All right. I would like to now invite the Muller Award Committee to ask any questions to any of the speakers, any of the 5 speakers. I know like some of the speakers didn't have enough time left at the end of the thing. So if all the speakers can kind of come online and Muller Award Committee can come online, this is the chance for asking any last questions.
I have a question for Ranel. When you showed slide 19 with the spatial distribution maps, was that the same data you showed in slide 8, where you identified the 1-1-1 pole? It looked different to me, but I didn't see it.
Right.
Yeah, so slide 19, where you show the SDM, was this the same data shown in slide 8?
No, these are different data sets. It's the same material, but it's different data sets.
So did you get an SDM from the data set that you showed here to confirm that 1-1-1 plane spacing?
Yeah, so I did that for every single data set that I analyzed. So here I'm just showing an example of the protocol, but yeah, so for every single one, I would follow this reconstruction optimization method. So I would really look at the spatial distribution map along each of the poles and compare their relative lattice spacing. And then once I had identified them, I would then calculate the image compression factor as well as the initial specimen radius to be able to get the accurate reconstruction.
Okay.
Yeah.
And then another question, and then I'll let the other committee members at it. So it seems like you showed 1D composition profiles from a couple individual clusters for the fluid inclusions. And I'm wondering what the reasoning was behind not taking, an average between all the isosurfaces of the same concentration, just to improve your statistics.
For the composition?
For the profiles, yeah. Composition profiles.
Yeah, I could have done that. I guess I wanted to show that they were high point density areas or features. Yeah, I didn't do it, but I definitely could have. And for
Seems like it would make your statistics more.
Yeah, it would definitely increase the statistics. But I guess in this case, I also wasn't so interested in the compositions of them yet. I was mostly interested in their morphology. So in that case, whether I analyzed one or all of them together, it didn't matter so much. But I agree, if you're looking for the compositions, then you definitely need to look at all the fluid inclusions and combine their contents for a composition analysis.
Okay, thank you.
I have a question for Martin. So you show this this tungsten tape experiment. Basically, I'm wondering, if you change substrate materials, and would you expect the result will change? Or if you change the specimen temperature, it's obvious. I mean, you see, you should expect this different ratio, etc. Right? So what I'm trying to think about is, could they use such a knowledge to generalize, say, to evaluate this ratio-based tool during this contamination of this chamber contamination, and we do the analysis in the matter because you use very lean technique of the straight flat pass, and not everyone has straight flat pass machine. I mean, my question is basically, you change the substrate, and how do you expect the result will change, and how to do a generalized this knowledge you achieved so far?
Yeah. So, well, the thing is, I guess we would need to try it out and run a different sample material. My thinking is that if we run materials that have a weak interaction with hydrogen, materials that are not these typical strong hydride formers like maybe steel or so, then I would actually believe that we observe similar results. And what's making me believe this is that in steel samples, at least the literature that's out there in voltage mode for deuterium investigation, they're very much seeing this, at least in voltage mode, the disappearance of the hydrogen 2+, and no such thing like a molecule, complex molecule that's then adding any weird special extra effects. And well, this is the fundamental for hydrogen imaging in steel so far. And deuterium, the tungsten observations, they are sort of in agreement with that, and therefore I would expect that steel is doing something similar. There's one problem to this, and this is that eventually, at least when you want to run below the evaporation threshold, then you actually need a high field material, because if your material is low field, then it will just start evaporating really quickly before you have captured any meaningful hydrogen spectra across different electric fields. Concerning the temperature, the problem with the temperature is this: if we try to run on the same tip at different temperatures, then we would need to heat up the sample, which on the one hand, it might lead to slight geometry changes because we have thermal expansion. And the second problem is that if we actually change the temperature in the experiment, there's all sorts of stuff that is boiling off as the sample heats up. Or if we go the other way, there's, the cryo will trap more residual gas, and that it will probably be difficult to ensure that these experiments at different temperatures are still very well matched. So I believe the way forward to check the temperature influence would probably be to start a completely new experiment on a new tip, and then see what the curve looks like.
Just one additional point. I'm wondering if they say this ratio, like you have this H2 plus to H plus and H2 plus, how this varies by the chamber pressure varies because we have a fluctuating chamber pressure.
Yeah, this I don't know how the chamber pressure influences this.
Okay.
Yeah, I'm sorry about that.
I just add a comment there on the same issue. When you did the data archaeology, there you could check for correlations between pressure and hydrogen.
That's true, yeah. I think a very, very long time ago, I've actually done that, but my sample size was 10 or something. And what I found is a lot of scatter and a reverse relationship. But yeah, I do agree. If now that we have a large number of data sets, maybe we might actually be able to see something in there.
Right, thanks. I have a question for Florent. I was thinking on the amount of carbon that you detect when you had the graphene on, was that on tungsten?
Yes.
Yeah. The amount of carbon atoms that match with the number of layers of graphene you have, or to me it feels like it's quite few carbon atoms on a graphene sheet or 4 graphene sheets. The number of atoms that you get, is that does that make sense with what you would expect?
Typically, I haven't been able to exactly correlate the number of the amount of carbon atoms that were measured to the number of layers. So I've tried several layers. So the samples that I showed here were 1 layer and 4, but I've tried with like 2, 3, 4, several numbers, and no, I haven't been able to correlate. But usually with higher number of coatings, there will be a larger volume of data in general, including the unavoidable layer of water that is also included in the process. Yes.
Yeah. Do you think you can get carbon atoms from, not from like the center or the tip, but maybe from carbon graphene flakes sticking out a little bit on the side or so? Also, so more carbon atoms than.
Yeah, so this is definitely a possibility. There was a relatively clean mass spectrum in general, indicating that most of the detected ions actually came from the tip. We had very sharp peaks. That being said, if when looking at the post-acquisition SEM images, there was a lot of graphene that was removed way further away from the tip than the actual size of the data set. So a couple microns away from the tip, the graphene was no longer visible in the SEM. So it means 2 things. Well, maybe also we can't just see it because graphene itself is very hard to spot. If it's laid flat on the surface of the sample, we can't see it. What enables us to see it is actually the defects and folds and things like that. So, but then there is an obvious difference between much further away from the tip, where there's still some like the large volumes, as was seen in the presentation. I'm happy to show the slides again. Yeah.
Yeah, thank you. Well, while I'm on it, I ask Hina a question also. So the tritium charged samples you had, they were, you said, stored for 4 weeks or something, and not using a cryo approach.
Yeah.
I mean, from what we've seen from many other work groups, is that it seems like cryo is necessary. Is that you think different binding of hydrogen in different cases, or where is the main issue that we maybe sometimes miss?
Yeah, this is something like I still feel that if hydrogen is present at a place, or if you, so for example, what we are doing with hydrogen embrittlement, we want to analyze the hydrogen that is leading to the embrittlement. it will lead to the embrittlement only if it goes to a specific site, like grain boundaries or something. And if it has to go to a specific site, and if you want to analyze it, whether it goes to the site under environmental conditions, then it should not that easily diffuse out. I mean, from my experience, I still feel that if a bulk sample is charged with deuterium, and after that we take its lift out in the fib without quenching it or doing anything, and then we analyze it, we should still be able to detect the deuterium segregated at a site, if it really goes to the site. By cryogenic transfer workflows, what we are doing, we are metastably trying to push it through, or we are trying to push it through into the site. But this way, we don't really know whether it is going to cause any embrittlement or anything, because that is not the mechanism by which hydrogen enters into the sites under the service conditions. I mean, in real service conditions, it is not pushed into the sample. That's what I feel. And also there is a question about reversible and irreversible trapping sites. So the hydrogen present at these reversible sites, which is the diffusible sites, when it goes there, that diffusible hydrogen causes embrittlement. The one which is present at the irreversible sites, that does not cause. This is something I still need to understand, that maybe the one which we can detect after several weeks or months, that might be the irreversible hydrogen trapped at irreversible sites, which might not cause any embrittlement, but that cannot be true for the grain boundaries. If I'm able to detect it boundaries, it has to be reversible. So I still feel that it can be done without the hydrogen which is leading to the embrittlement can be detected without cryogenic transfer workflows.
Thank you very much. I leave the floor.
I had a follow-up to that. I'm also surprised that the tritium was so available without cryotransfer after 4 weeks. And I was just wondering if you had any examples from the literature of deuterium charging sites that maintained that without cryotransfer.
So from the literature recently on aluminium,
or your own work. I mean, you went through the effort of cryotransfer for your deuterium charging, but it sounds like you don't believe that that's necessary.
Because that was my last conclusion.
Okay.
What I could find after doing all those things. So
it'd be interesting to have that.
Necessary what I did for 2 years.
Sure.
So, yeah. So what I did here was the deuterium the tritium charge was the without transfers, but the deuterium charged ones were with the cryogenic transfer workflows, the grain boundaries. But there I charged the atom probe specimens in the reactor hub, which was the gas charging chamber. Not sure if maybe I need to share the screen again. So this was done because here I was trying to charge the atom probe specimens. This was because in that gas charging chamber, we can go to only very low pressures, like 250 millibars it was done. And at those low pressures, you cannot charge the bulk samples. And also in that chamber, we cannot really introduce the bulk samples and do it. So that's why I had to do it on atom probe specimens. But on the tritium charging was possible on bulk samples at Karlsruhe. That's why it worked. So from the literature, there is a recent paper on aluminium, which maybe I can try to share at the chat, the link to that paper, which is by Mahdi. This is also from MPI, the recent. Where they actually found not the deuterium, but hydrogen without doing any cryogenic transfer workflows, and they could find it.
That's okay, Hina. I just wondered, why go through this if it's not necessary?
Yeah, I mean
it's a reasonable place to start for
this
sure.
Was the paper on aluminium, which I just shared.
Okay, thank you.
The samples were analyzed after like 2 to 3 years. They were already subjected to the stress corrosion cracking of aluminium alloy. And they still found the hydrogen at dislocations here, but here they have the edge dislocations, so they could find it. So you cannot charge with hydrogen because there is always a peak at 1. But I think if we charge a bulk sample with deuterium by any means, whether it is electrolytic charging or gas charging mean, and then we can, if we do the fib lift out and we analyze it, we should still be able to find it at the trapping sites where it is trapped. And then with the field evaporation conditions and charge state ratios between the uncharged and the charged samples, we can do the analysis and we can make sure whether this deuterium is not from the, like, this is not H2 molecule from chamber. So this is something I feel it can be done, which I would like to do in future on different materials.
I also have a question for Hina. So basically, your project involved with deuterium charging electrochemically and deuterium gas charging and trillium basically charging, but I don't know exactly the mechanism. And you have a 3 different set of charging system. And how would you evaluate that? Because essentially, electrochemical charging, you are putting protons inside the materials. And this would have a different interaction compared with deuterium gas molecules or trillium gas molecules with the vacancies or burn boundaries, etc. And how would you evaluate how this charging mechanism that would influence on the say the hydrogen trapping size? I mean, because essentially you have a different trapping size and the different interactions with protons and gas molecules. How would you differentiate the difference, or how would you evaluate that?
So electrochemical charging I use for the bulk samples after which the tensile deformation was done. This was not done on, like, on atom probe samples. I tried the electrochemical charging, but it did not work. So I am not analyzing any atom probe results from the electrochemical charging. Atom probe are on from the deuterium charging and from tritium charging. So I mean, both of them are not really comparable. This is true. What we can say is that whether there is a deuterium segregation at a grain boundary or at a tritium segregation at a grain boundary, but this implies the hydrogen segregation at grain boundary, which leads to the embrittlement. So this is something one can say from this. But electrolytic charging, which was done on bulk samples. So in bulk samples, when we compare the deformation behavior, whether you compare with so I mean, in this bulk samples, if you charge by the gas charging, the charging is not really efficient. And that's why I use the electrolytic charging to introduce more hydrogen into the bulk samples so that the deformation behavior can be compared. But the deformation behavior will be same whether you introduce the hydrogen or deuterium or tritium.
Mm-hmm.
I had a question for Ranel. I was wondering if you could describe your specimen preparation protocol, and also if you did any site-specific preparations.
Yeah, so I don't have the slides ready, but I did the traditional like Toblerone bar lift out by milling on either side, and I did most of the milling in a gallium fib, and I typically tried to avoid gallium implantation by finishing the milling process with a low kV shower, so either at 2 or 5 kV. And I did site specific, so I simply, most of the grain boundaries I was able to see or most of the features I was looking for, I was able to see in the SEM images. And so I simply put markers down or put a platinum layer down on the site of interest to make the lamella lift out. I don't know if you were looking for more details. I don't have the images ready.
I was just wondering, just because I think we didn't catch that in your presentation. So if there were any particular challenges that you ran into, you could also mention that. otherwise that answers my question. Thanks.
All right, I have one for Olga. You did not go much into the carbon, but I guess in the Martin site, do you see it enriched at left boundaries or dislocations, or?
Yes. On we just did not treat the carbon because we are interested in austenite ferrite transformation, phase transformation, and after during the quenching and during the just keeping for room temperature, carbon can segregate. So we cannot separate this segregation at high temperature and room temperature or quenching. But indeed, we have a lot of very interesting data also related to the carbon segregation. As you mentioned, the segregation on loss, on dislocation, and also one is the interesting effect that depending on which orientation relationship on the investigating interface, this carbon peak can be displaced with respect to the manganese peak, because in most of the case it's on the same position, but at some particular condition we observe this situation. So there is also a lot of interesting issue that can be discussed.
Yeah, so you don't believe that there is a problem detecting carbon, it's just that you don't know if it was doing things during transformation or later during.
Yes, it's not a problem of APT. It's one of the advantages of APT that it can detect carbon. It's just the problem of our specific task, that what we want to see.
Exactly, makes sense. Thanks.
Thank you.
Well, then I could add one to Martin also. You were changing the frequency. I didn't see an effect on that when you do evaporation below the threshold of the needle. I guess if you do it while evaporating the needle, then you see often a difference in hydrogen, right?
The hydrogen per time is constant. So basically, so it depends on how you see it. The time of the hydrogen per time is constant, which means that APT data set that is run in a shorter amount of time, it will contain less hydrogen. But of course, then naturally the amount of contaminant hydrogen per pulse, it is then of course not constant, because if you're pulsing faster and you're running faster, then let me think this through. Oh no, yeah, it's time of flight constant, not pulse constant.
And then you were looking at what you presented was the ratio between H2 and H.
Yes.
I mean, often we're also interested in the absolute or the absolute concentration of hydrogen relative to the base material. And in that case, I also think the frequency plays a role. You have less time to get the hydrogen.
Oh yes, the time constant supply. Also, there's one more thing in there, is the total amount of hydrogen in laser mode is higher.
Yes. Right, thanks.
Okay, thank you. I think, Dong, do you have any additional questions?
If we still have time?
Yeah,
no time.
There's a bit more time.
Okay, yeah. I have a question to Ranel. So you make this simulation of this, how do you call this, liquid clusters inside? Inside your material, and you saw this oxygen as just one single slice on top of every single liquid cluster. And you make this a simulation, you think that this is a kind of a low field materials, and once it's going through this layer, all of a sudden it's just like a burst is going to the detector. And the thing is, I'm curious is if this is really a liquid, and in the analysis condition, that should be turned to solid part. And it will be very difficult for such a low field species to like burst going out of the sample. And how would you correlate this simulation with your material? This is real liquid, or this is like dust bubble, etc.
So yes, under the analysis conditions for APT, the fluids, whether they're usually fluid inclusions, are a combination of gas and liquid, as well as sometimes solid salt crystals within the fluid inclusions. But under APT conditions, it will definitely be ice. However, since I did this study, there's been a few publications on the field evaporation of frozen water. So from the team in Stuttgart, as well as MPIE in Sydney. So there's, they have been able to show since then that the evaporation field of water is very low, which is consistent with the simulations for our data set. So we didn't have those data at the time, but now we do.
Okay, and on the other hand, it's because your matrix material is iron sulfur and I mean iron S2 basically. And how did you distinguish the sulfur peak and the oxygen peak here? Because essentially you are analyzing this red cap is from oxygen signals, but it could also be the sulfur peaks.
The oxygen that I reconstructed is not only the oxygen at 16, it's really the decomposed peaks. So any ions or any peaks that contained oxygen within the molecule, I decomposed it and used those oxygen ions to do or to make these isosurfaces in reconstruction.
Okay.
So it's it's not only coming from the 16 peak.
Yeah, thank you.
Okay, assuming all the questions are answered, thank you very much for the Muller Award Committee to be here, and all 5 presenters. Thank you for the excellent talks and really answering questions very effectively. It was fantastic competition today. It was my honor to chair the Muller Award competition as the VP of IFIS. The Muller Committee has a difficult job of selecting one winner. So they will deliberate on the scoring, and we will try to announce the decision soon. But I would like to now then conclude the Muller Award presentation. Thank you for everybody's presentation, great talk. And I would like to hand it over to Gang Shah.
Okay, yes. Okay, thank you for your fantastic to host this this session, the Muller competition. All the speakers gave an excellent talk. Also, the committee members asked very nice questions. The discussion is very interesting. So I'm very happy to attend this afternoon session. So next, we just wait 5 minutes. We will come back. Then we will announce the next APT&M 2023. So I think Claudia will give a presentation about the next APT&M conference. Okay, so we just have 5 minutes break, then come back. Okay, thank you all.
Is Claudia here?
Yeah, I have. If I look at the list, it seems he is here, but I sent any message. He didn't reply. If I check, the list, Claudia.
Hi, Claudia, are you here? If you are here, can you respond? Oh, there she is.
Yes. Good. That's great. So we just come back in 5 minutes. You can, yes, that's good. Okay.
Okay, my sound works.
Yeah.
If you want to try sharing your screen, that might be good.
Yeah.
Okay. Hello, everyone. Hear me? Okay, I think we will move to the next part of today's program. We will make an important announcement about the next APT&M conference. It is called APT&M 2023. So I will hand over to Claudia Friedman to make her announcement for the next APT meeting, and he will show some files about Belgium, I think. Okay.
Yes, thank you so much for the nice introduction. The name was almost right, Fleischmann, but it's a difficult one. I promise I don't keep you for much longer. You have spent already a long time listening to very exciting talks. I'm very excited to announce that conference. First of all, it's the first conference, the first APT&M conference I am organizing together with my colleague André van Tomme. And it's also the first in-person conference we have after a 5 years break. I feel it's pretty long, but we did the calculation over and over again. It has been 5 years since we haven't met in person. So bear with me, I want to show you a short teaser why we think you should come to Leuven in Belgium, and then I give you some more details. So just a few seconds. So I hope you have seen a short movie to introduce Leuven to you. I would like to go through the slides in a few minutes to give you a little bit more details about the Leuven and the conference. And feel free to also check our website afterwards, which will contain all of the details and which will be also updated regularly. So I will quickly switch to my presentation, which I hope will work smoothly. Okay, I don't see any feedback. I hope you will see my slide. Could someone please give me a short feedback here?
It's working fine.
Yes, it looks good. Yeah.
Thank you. Okay, so let me go to the starting slide. So the conference, which will be actually the 16th International Field Emission Society meeting, will be hosted in September, 17th of September till 21st of September in 2023. And we, that is Professor André van Tomme from the University of Leuven and myself, Claudia Fleischmann, from the University of Leuven and also IMEC, would like to welcome you to Leuven. Now, where is Leuven? Indeed, you mentioned that already quickly. Leuven is in Belgium, and Leuven is actually only half an hour away from Brussels, but also very interestingly, just a few hours away from most famous European capital cities. Leuven is a very small but very lively city with many facets. It has been announced the best European destinations in 22, and I'm sure also in 23 it will still be very interesting and fun to visit the city. Now, Leuven is the eighth largest city in Belgium. It has around 100,000 people with 50,000 students, and that also obviously make the city lively and drive the city. So Leuven is really largely dominated by the university, which was founded in 1425. So if you want to come back in Leuven, I think in 2025, it's a good timing. That will be a big party here. So many buildings in Leuven are erected in that area, and they still have survived and give Leuven the very, very nice, unique and historic character, as you can see also here in some of the images. Now, we have, how do we come to Leuven? We have two main airports, but I would like to highlight that we have actually very eco-friendly versions, like very good train connections, with Eurostar, TGV, Thalys, also the German ICE, Deutsche Bahn, and also very good bus connection with the typical lines like Flixbus and blah, blah, plus to reach Leuven in an eco-friendly way. How do we move around within Leuven? Leuven has a very small historical city center, which is traffic-free apart from the buses and the taxis. Only bikes and pedestrians are allowed in the city center. It is very small, so you can walk everything. And especially the most important points like hotels, the conference venues, shops, and all you need, restaurant, will be within walking distance. It is also a very safe city to walk there. And there is always something happening around the clock. Leuven has, of course, numerous restaurants and bars. As I mentioned, it's driven by our students in the cities. Restaurants you need, if you come here, you must try, of course, the French fries, which are very famous. And if your budget allows, you can also jump into one of the Michelin star-rated restaurants we have in Leuven. Now, I cannot really comment on that. I usually lean to that side. And there's also really, as you can see here in the streets, there are plenty of restaurants and bars to spend your evening to discuss and chat with colleagues and reconnect after the official conference. Now, in view of hotels, of course, we have the typical hotel ranges as every big city has, and we will also make sure that we can find attractive low-budget accommodation to also allow students from our community to really come to this first, maybe for them, first in-person conference here in Leuven. As I mentioned earlier, the conference venue will be located in the city center, so everything is within a walking distance. We have chosen the so-called Maria Theresia College, which is also a very historical environment, but still directly in the city center, but also still very up-to-date in view of the amenities and facilities in there. What is on the agenda now? It will be a typically APT&M meeting. Also, I would like to highlight that we have, apart from the block lecture, the award competition, as we just had now, poster sessions. We will also have ISO standard meeting. We will have a workshop, and we will have welcome reception, a conference dinner, an excursion, a lab tour or a clean room tour. But overall, I think the general theme of the conference will be to allow to reconnect or connect and network with our colleagues again in person, so that we'll have plenty of opportunities to discuss, to chat, to exchange, and so on. So here's just a short teaser about the conference activity. We will choose a very nice, one of the nice cities we have here available in Belgium, where we have a nice Wednesday afternoon for an excursion. More details will follow about this. And then this is also already my last slide. I would like to highlight, as I mentioned throughout the presentation, the big word here is that we do big efforts to keep our carbon footprint small. So we also encourage the attendees to choose for eco-friendly options, and we also do a lot to choose for eco-friendly options during organizing the conference, the materials we use, the caterers we use, and so on. I'm also investigating still option if maybe we could support an earth-friendly project, because indeed flying in, some of you cannot take the train options. Flying in will add to the carbon footprint, but maybe we can compensate for this. And with this, I think this is already, I leave you to the break. That's all what I wanted to say. Check out our website with latest updates. Reach out if you have questions. Note already the date that you make sure you are available, and share it with your friends, colleagues, and networks so that everyone is available and can join us. That's all. If you have questions, shoot. Thanks for listening.
Thank Claudia for its very interesting introductions. I'm really looking forward to go to Belgium, Leuven, to attend the next APT conference. Yes. Also, I think now we can conclude today's other programs. I would like to thank all the speakers to give very excellent talks. Also, I would like to thank all the chairs who worked hard to manage the time. Also, I would like to advise all the participants just visit our website, conference website, to get the updated program. Because some talks we just receive the message and ask not to record it. So for those talks, we will not record it and we will not release it in YouTube. So if you want to listen to that talks, do make an effort to attend those talks. Okay. Thank you all for today's participants. And so I will see you tomorrow.